Well, welcome to the second tutorial of CARDIS. So this is Jean-Sébastien who will be giving this tutorial. So Jean-Sébastien Coron is a professor at the University of Luxembourg. And in the past 20 years, he has been working in about all the areas of cryptography, I think, and doing pretty important work. But in the last years, he published with co-authors a series of papers about masking scheme of post-quantum cryptography, and this is what he will be talking about today. Here you go. Yeah, you can take the mic if you want.
Yeah, so thank you, Thomas, for this introduction. So good morning. So today I'm going to speak about the challenges of securely implementing post-quantum algorithms, and in particular lattice-based algorithm to get security against sidechain attacks. So let me give an overview of my talk. So the first part of my talk will be a general introduction to post-quantum algorithms with an overview of the main categories of post-quantum algorithms, and we will focus on the Kyber and Dilithium schemes, which have been recently standardized. And then I will speak about the challenge of sidechain attacks and the threat of sidechain attacks, which are obviously still relevant for post-quantum algorithms, and in particular for Kyber and Dilithium. And I will then, in the third part of my talk, describe which side-channel countermeasures we can have. So first, I will speak about the security model to get higher order security, and then I will describe one of the main tools to implement masking for lattice-based schemes, which is the conversion between Boolean and arithmetic masking, and then I will explain how to apply this to Kyber and Dilithium. So that's the overview of my talk today. So first, the motivation for post-quantum cryptography. So as you know, public key crypto is based on hard problems. So for example, RSA is based on the hardness of factoring, n equals p times q, and ECC is based on the hardness of the discrete log problem in the elliptic curve. And so we don't know any classical any algorithm to break these schemes and to solve these problems efficiently, at least on a classical computer. But as you know, if we have a quantum computer, then we can break RSA and we can break ECC. There is this Shor's algorithm, which was discovered 30 years ago, that can break RSA and ECC, assuming that we have a large-scale quantum computer. So these problems are broken by a quantum computer. And so, of course, we must find countermeasures, but fortunately, a quantum computer cannot break everything. As you know, there exists problems which we don't know how to solve, even with a quantum computer. And so the goal of post-quantum cryptography is to design new schemes based on these problems to be secure in the post-quantum era. So fortunately, we know many such problems, and now I'm going to recall the various categories of post-quantum algorithms. So one of the first alternative to RSA was the Makelis scheme, which is based on codes, and which was invented more than 40 years ago. So its security relies on the hardness of decoding general linear code, and for this, we don't know how to break this even with a quantum computer. So this leads to the Makelis encryption scheme, but one drawback is the large public key size. And then there is the crucial field of lattice-based cryptography. So lattice-based is based on the hardness of solving certain problems on high-dimensional lattice. So mainly the shortest vector problem and the closest vector problem. And one early scheme is the N-true scheme, which was designed in 1996, which is a very fast public key encryption scheme, so based on lattices. So another family of post-quantum schemes is the multivariate cryptography, where the first scheme was the Matsumoto Imai C-star scheme, designed in 1988, and then the HFE scheme by Patarin on 96. And so in this case, the security relies on the hardness of solving systems of multivariate polynomial equations over a finite field, and for which we don't have which we don't know how to solve even with a quantum computer. And one advantage of this family of schemes is that it provides very short signatures. And then we also have the hash-based cryptography initiated by Lamport more than 40 years ago. And so this enables to design digital signature schemes based on the security of hash functions. So we only have to assume that the hash function is collision resistant. So this enables to avoid relying on more structured mathematical assumptions like finding a short vector in a lattice. So here we only rely on the hardness of finding a collision. And so let me say a few words also about the NIST competition. So as you know, the purpose of the NIST competition was to standardize post-quantum algorithms. So for both encryption or key establishment and for signatures. So the competition was initiated in 2016. And in the first round, there were 82 submissions. And after a review in 2018 or 19, I think there were only 26 candidates for the second round. And eventually at round 3 in 2020, there remained only 7 finalists and 8 alternates. And so, and eventually for the third round selection in July 2022, Kyber was selected and was selected as the new standard. And the new standard the standard has been drafted recently. So that's for public key encryption. So Kyber for public key encryption, which is lattice-based. And for signatures, so Dilithium and Falcon have been selected, and they are both lattice-based. And also Sphinx Plus has been selected, which is hash-based. So, but in this talk, I will focus mainly on the Kyber and Dilithium schemes. So, but for the transition to post-quantum cryptography, what is recommended by both ANSI and BSI for this transition is to use hybrid cryptography. So it means that we are going to combine 2 or more crypto systems together. And so to use both a classical crypto system, so for example, RSA, and a post-quantum algorithm to provide robustness. So in that case, if we have a quantum computer, then we are protected, we are still secure thanks to the post-quantum algorithm. But on the other hand, we have less experience in implementing post-quantum algorithms. So if there is a sidechain attack against the post-quantum algorithm, so for example, against Kyber, then we are still protected by the sidechain resistance of RSA or ECC, for example. So how does it work? So for a key establishment mechanism, we are going to generate a session key, but it's going to depend on both the session key generated by the classical algorithm. So for example, here we have RSA with the public key of RSA, and we have the key establishment mechanism that encrypts a random session key, and which gives us a ciphertext. And same for Kyber. We have the key establishment of Kyber, which generates a ciphertext with session key K2. And then the session key, the global session key, is generated by hashing K1 and K2. So this means that to decrypt, to recover the session key, you must know both the private keys of RSA and the private key for Kyber. And so, if one of the 2 systems is broken, then you are still protected by the other one. And for signatures, that's the same approach. We simply concatenate the 2 signatures, the classical and the post-quantum signature. And in that case, the signature is verified if both signatures are verified. So let me focus on the Kyber post-quantum scheme. So it's a key encapsulation mechanism in which we encrypt a random session key to get a ciphertext. So the security is based on the hardness of certain problems based on lattices. And so the goal with Kyber was to get a security level equivalent to RSA, but of course being resistant to quantum attacks. And so the security is based on the module learning with error problem, and I will explain later what it means. So that's for Kyber. And so let me say a few words about Dilithium and Falcon signature schemes. So both signature schemes, which have been standardized by NIST, Dilithium and Falcon, are based on lattices, so for security against quantum attacks. And so, but they are based on two different techniques. Dilithium is based on Fiat-Shamir with a board on module lattices, whereas Falcon is based on hash and sign on n-true lattices. But both are designed to have a relatively small key and small signature. So the goal was to minimize the combined size of the public key and the signature. So what's the difference between the two? So one advantage of Falcon is that it provides slightly smaller keys and signatures compared to Dilithium. But one drawback of Falcon for side-channel attacks is that Falcon requires Gaussian sampling, which appears to be hard to secure against side-channel attacks. So eventually, the Dilithium is the primary signature scheme recommended by NIST for post-quantum security. So of course there are side-channel attacks. So as you know, with side-channel attacks, so there are many different side-channel attacks: timing attacks, power attacks, electromagnetic attacks, and we can when we use this side-channel and when we perform statistics, if there are no countermeasures, then of course we can quickly recover the secret key. And obviously this applies as well to post-quantum algorithms, and post-quantum algorithms such as Kyber and Dilithium are of course vulnerable to side-channel attacks. And so we must find countermeasures, but we have of course less experience than for securing RSA and ECC, and so there are new challenges, and so there is a variety of algorithms and of techniques. So today I'm going to describe the basic techniques to protect Kyber and Dilithium against side-channel attacks. So, but let me say also a few words about the lattice-based cryptography and the hard lattice problems in cryptography. So what is a lattice? A lattice is basically a regular grid of points in a high-dimensional space, and which is defined by a basis of vector. And so we can define many problems on a lattice, and the most important one being the shortest vector problem. So we are given as inputs a lattice basis, so for which can be relatively long. So for example, this basis in blue, and the goal of the shortest the shortest vector problem is to find the shortest non-zero vector in this lattice, and it is believed that this is hard even for a quantum computer. So we don't know any classical algorithm, but even with a quantum computer, this remains hard. So we know some approximate algorithms, and the most famous one is the LLL algorithm, but it only provides an approximation in polynomial time. So you don't necessarily get the shortest vector, but only a reasonably short vector. And of course, for the design of a post-quantum algorithm, such as Kyber and Dilithium, one must tune the parameters to make sure that LLL cannot recover the shortest vector in polynomial time. And so in general, finding the shortest vector has exponential complexity, exponential in the dimension of the lattice. So by using large enough parameters, we are guaranteed that recovering the private key is infeasible. And so more specifically, what are the hard lattice problems that we are using in crypto? So the lattice problems are based on the learning with errors problem or some variants. So what is the learning with error problem? So we are given a matrix. We are given a matrix A of integers modulo Q, such that A times S. So we have a linear combination of the columns of the matrix, which is equal to E, which is small. So we have a small. We know that there exists a small linear combination of the columns of the matrix, which is small. And then the problem is to recover S, to recover this small linear combination. And there are variants of this problem, mainly the ring LWE and the module LWE. And these are variants in which the secret and the elements of the matrix, instead of being only modulo Q, belong to a polynomial ring. And the main advantage is, as we will see, is efficiency. So why do we base our security on these problems? Is that there is a reduction from the worst case lattice problem. So this means that if you can solve this problem in parallel time, then you could find, so you could basically solve the shortest vector problem in a lattice, which we don't know how to solve. So this means that these problems should be hard. And so this is believed to be hard against, as I said, both classical and quantum adversaries. So let me describe maybe in a bit more details how to encrypt with based on the learning with error problem, and then I will explain. I will recall also the Kyber scheme, which is based on a variant of this problem. So how does it work? The secret key is simply a vector of n elements modulo prime q, and for now we are only encrypting a single bit. So we are the message M is a single bit. So an encryption of this bit M is a vector of elements modulo q, such that the scalar product of this vector with the secret key is something like this. So E, which is small, it's called a small error, plus M, so the bit M, times Q/2. So so here this is illustrated. If we perform this, if we have the row vector C that we multiply by the column vector S, we get something which is E plus M times Q/2. So this means that the message M is encrypted roughly in the most significant bit modulo Q. So that's for encryption. And how do we decrypt? So we simply compute this scalar product C times S to recover E plus M times Q/2. And then we apply a threshold function, because if the bit M is 0, since the error is small, we expect this value to be around 0 here. On the other hand, if the bit M is 1, we expect to be around Q/2, plus because the error remains small. So we apply this threshold function. If we are between 0 and Q/4, or pre-Q/4 and 0, we say that the bit is 0. Otherwise, we say that the bit is equal to 1. So far, I have only described a symmetric key encryption scheme, because to encrypt, we need to know the secret key, but it's easy to turn this into a public key encryption scheme. So for this, what we do is we simply publish a set of encryptions of 0. So we still have the same secret key S, but for simplicity, we assume that the first component of the secret key is 1. So it has n components, but the first component is 1. And for the public key, we use a matrix A such that A times S equals E for a small e. So this corresponds to the learning with error problem. And so this means that every row of A is actually a ciphertext LWE encryption of 0. And now to encrypt, what we do is we simply take linear combinations of the rows of this matrix. So that's why we left multiply by a vector of small components here. And so this takes a linear combination of the rows of the matrix. So a linear combination of the ciphertext, which are encryptions of 0. So this remains an encryption of 0. And then at the end, we add Q/2 times M and 0, 0. So this vector, which is an encryption of M, because the first component is 1. And so eventually, we obtain a ciphertext, which is an encryption of the message M. So now, as you see, we have obtained a public key encryption scheme, because to encrypt, we only need to know the public matrix A. And of course, the decryption remains the same. We still compute this scalar product with the private key and apply the threshold function to recover the bit n. And so, as I said, there are variants of this scheme which are more efficient, because here we are only encrypting a single bit at a time. So to encrypt multiple bits at a time, we can use the ring LWE problem, in which we, instead of computing only modulo Q, we use a polynomial ring. So we work with polynomials with coefficients. All the coefficients of the polynomial are modulo Q, and the polynomial is defined modulo this polynomial x to L plus 1, where generally L is a power of 2. So this means that this forms a ring, which means that we can add and multiply such polynomials. And when we perform an addition or a multiplication, we reduce the coefficients modulo Q and also modulo this polynomial x to L plus 1. So it works the same as previously. The only difference is that our elements belong to this ring of polynomials instead of just modulo Q. And now the main advantage is that we can encrypt a message M, which now is a polynomial of degree at most L minus 1 and modulo 2. So we encrypt a polynomial with binary coefficients. So instead of a single bit. So this means that this provides much more bandwidth, because so for example, for Kyber, we are using L equals 256. So we can encrypt with Kyber 256 bits at a time instead of a single bit. So this is much more efficient. And now the security is based on the ring learning with error assumption, which is we are given T and A. So A is a random element in the ring, or Q, and S and E are small secret elements with small coefficients, so polynomials with small coefficients. And we compute A, S plus E, we are given T. So given T and A, it should be difficult to recover the secret key S. So that's the ring learning with error assumption. So let me explain. So I'm going to explain how encryption works based on the ring learning with error problem. And because Kyber is relatively, as we will see, is relatively similar. So the key generation is what I have said. So we generate a random polynomial A in the ring and small s and e. And so the public key is T A S plus E and A, T and A. And now the public key encryption of a message M. So this time M is a polynomial of degree at most L minus 1. So a polynomial with binary coefficients. So what we do is, so the ciphertext has two parts. So we compute A times R plus E1 and T times R plus E2 plus Q/2 times M for small polynomials E1, E2, and R. And then to decrypt, so when we have this ciphertext with two components, U and V, to recover the message M, what we do is we compute V minus S times U. So V minus S times U is a polynomial. And it's easy to see, to check that this polynomial has a special form it can be written as Q/2 times M for the plain text polynomial plus something small. So this means that we get a polynomial here of degree with L coefficients, and for every coefficient of this polynomial, we have something which is either 0 or Q/2, because M is a binary polynomial, so every coefficient is either 0 or 1, plus something small. So this means that we are going to recover the message M. We are going to proceed as previously. We are going to apply the threshold function to recover every bit of the message polynomial. Either we are around 0 or we are around Q/2, and so eventually we can recover the L coefficients of the message M. So that's basically RISC-V public key encryption. And so now I'm going to describe quickly the Kyber scheme. So in Kyber, we are working in a fixed polynomial ring. So with degree 256, and with a fixed prime Q. And the security of Kyber will depend on the size of the vectors and the matrices that we are going to use. So we are going to use vectors of dimension k and k by k matrices of ring elements. And so and then the security level will depend on the value of k. So we are using always the same underlying polynomial ring, but the security depends on the size of the vectors. And then the security of Kyber is based on the variant of the ring learning with error problem, which is the module learning with error. So, but it's almost the same as previously, except that instead of using so we are working with vectors and matrices. So we are given a matrix A here, where the elements of the matrix A are elements in the polynomial ring here, and we are given also so we generate a vector S with small polynomials and an error E with small polynomials, and we compute the matrix vector product AS plus E, which gives T, and the module learning with error problem is given A and T to recover S. So and so it should be hard to recover S given A and T. And so I'm going to quickly describe the Kyber scheme. So to generate the key for Kyber, we generate such matrix A and so small vectors S and E, and then the public key is A and T, and the secret key is S. And to encrypt with Kyber, it's the same, almost the same as ring learning with error encryption. So we generate the small errors R and E1 and the small polynomial E2. And so the ciphertext again has two parts, but this time the first part is a vector of elements, which is A transpose times R plus E1. And the second part of the encryption is a polynomial, and which is completed like this, in which we embed the message M. And to decrypt, it's almost the same as previously. We compute V minus this scalar product, and then this is a polynomial with 256 coefficients. So we are going to apply, to recover the message M, we are going to apply our threshold function on every coefficient independently to recover the 256 bits of the message. So that's basically how Kyber basic encryption and decryption works. And but of course here I have only described the basic Kyber scheme, which is only secure against a chosen plaintext attack. So we only get CPA security. So what does it mean? It means that given only the public key, and a ciphertext reveals no information on the plain text. We have the indistinguishability of encryption property. But actually, what we want is we want to reach a higher level of security. What we want is to be secure against chosen ciphertext attack. And in the previous scheme does not achieve chosen ciphertext attack security. And so what does it mean? It means that the attacker is more powerful. The attacker can also submit ciphertext to be decrypted. So the adversary has access to a black box in which he can submit ciphertext, and he gets the corresponding plain text. And of course, he knows the public key. But he has additional access to this chosen ciphertext black box. And eventually, the attacker must, for example, recover the secret key or be able to decrypt another ciphertext, which he cannot submit to this black box. So in general, how do we achieve chosen ciphertext security? There is a generic transformation which is provided by the Fujisaki-Okamoto transform to transform a basic scheme to be chosen ciphertext secure. And how does it work? As we will see, the technique is to verify the correct decryption by re-encrypting the message. So first, we decrypt the message, and then we re-encrypt it to check that it gives the correct ciphertext, the same ciphertext from which we have started. So let me describe this more concretely. So assume that so this basically describes the chosen ciphertext secure decryption using the Fujisaki-Okamoto transform, which is used, for example, in Kyber. And so given the ciphertext C and the secret key S, the private key S, we first decrypt using the basic decryption procedure of Kyber. So we get a message M, and then we want to re-encrypt the message M. But so for this, the randomness which is used to encrypt the message M actually depends deterministically on the message M that is encrypted. So instead of using randomness, of generating the randomness independently, when we encrypt, the randomness is generated from a hash of the message M. So this means that we know the randomness, and this means that we can re-encrypt the message M to get a ciphertext C prime, and normally the ciphertext C prime should be the same as C. So we make a test. If the two ciphertexts are the same, then we can return the session key, which is derived from the message M that has been decrypted. So if the two ciphertexts are the same, then in that case, we return this session key K. Otherwise, we return nothing, or we return a random session key, as it is done in Kyber. So this means that the adversary cannot modify the ciphertext C. So if the ciphertext C is slightly modified, what happens is that it's even if the decrypted message remains the same, what happens is that the two ciphertexts will be different, and the adversary will not get the session key. So it will get no information about the message and no information about the private key. So this is so with this construction, we can prove that we achieve chosen ciphertext security in the random oracle model. But of course, there are side channel attacks, and we can perform side channel attacks against the Fujisaki-Okamoto transform. So actually, there are many components in this Fujisaki-Okamoto transform. So many ways of breaking it. So one can attack directly the basic decryption scheme to recover the private key, or we can also attack the re-encryption phase of the message M, a template attack, or we can also attack the ciphertext comparison. And so and in all these cases, without side channel countermeasures, we can recover the private key. So to illustrate this this side channel attack, I'm going to describe this later attack against the ciphertext comparison in the Fujisaki-Okamoto transform. So the attack is based on the decryption failure attack. So what we know is that without the Fujisaki-Okamoto transform, it will be easy to perform a decryption failure attack. So what we could do is, starting from a regular ciphertext C, we can submit a perturbed ciphertext C prime, which is the same as C, but plus some small error delta. And in that case, we assume that we can obtain the decryption of C prime. And then we compare this decryption C prime, the decryption of C prime, so M prime, we compare it to the original message M. And we assume that we can know whether the message M, so M prime remains the same or is different. So due to the way lattice decryption and lattice decryption works, we expect that if the error delta is small, then the message M is not going to be modified. So M prime will be the same as M. But at some point, when the error delta becomes too large, N prime and M are going to be different. And so we assume that we can learn this bit of information, and which we call a plain text checking oracle. So we can check whether M prime remains the same as M or not. And in that case, so without the Fujisaki-Okamoto transform, it's easy to see that we can break the scheme thanks to this additional this oracle, this plain text checking oracle, because by doing a binary search, we can recover this scalar product of C and S, and this gives us a linear equation in the private key, and eventually we can recover the full private key. So normally with the Fujisaki-Okamoto transform, we cannot perform this attack, but still with side channels, we can perform a template attack. So for example, a template attack, as is done in this paper, on the ciphertext comparison. And as I will explain, this provides actually a plain text checking oracle, exactly as previously, from which we can recover the private key. So let me describe the attack in a little bit more details. So let me describe first the decryption failure attack without the Fujisaki-Okamoto transform. So we assume that we have an attacker. So for simplicity, I'm going to focus on simple LWE encryption, in which we only encrypt a message M, a single bit. But it works the same with Kyber. So we assume that we have an attacker who can submit a ciphertext C and obtain the decryption M, which is the threshold of C times S modulo Q. So now the attack works by submitting a perturbed ciphertext C prime, which is the same as C plus some error on the first component. So this means that when we decrypt C prime, we get a message M prime, which is the threshold of C prime and S, so which is CS plus E. So this means that the error modifies the value of this scalar product. So for example, we can in this circle, we can go from the zone of 0 to the zone of 1. And so that's why it's easy to recover the secret key by using a binary search. So we are going to by a binary search on E, we can find where is the threshold. At some point, we cross the threshold, and the message M becomes 1 instead of 0. And so eventually we can recover this value exactly, and eventually with n such equations, we can recover the secret key S. So that's how decryption failure attack works without the Fujisaki-Okamoto transform. But now, so of course, this attack is prevented by the Fujisaki-Okamoto transform, but we can still perform a side channel attack on the Fujisaki-Okamoto transform. So how does it work? So we still submit a perturbed ciphertext C type C plus delta, and then we expect that if the delta is small, it's going to decrypt to the same message here. So which means that it's going to re-encrypt into a ciphertext C prime, which is almost the same as C tilde, except for the small perturbation delta. And so this means that we expect that there is only one coefficient which is going to be different. Otherwise, if delta is much larger, then it's going to decrypt to a completely different it's going to decrypt to a completely different message M. And so so in that case, all the coefficients of the two polynomials, C prime and C, will be different. And so we can actually detect this using a template attack in the ciphertext comparison. And so this means that we can detect whether the message M remains the same for the perturbed ciphertext or is different. And so this gives us a plain text checking oracle. And so we can apply the previous attack and eventually recover the private key. So that's an example of such an attack against Kyber. So this means that actually we must protect and we must apply sidechain countermeasures. So the most basic sidechain countermeasure is masking. So we want to mask all variables which are dependent on the private key. So this means that here in this picture, so the private key itself must be masked, but the message M that is being decrypted must be masked. And when we re-encrypt it, the ciphertext C prime must also be masked because it depends on the private key. And also the randomness R, and of course the session key. And so this means that the ciphertext comparison also itself must be masked. So basically we must mask everything. And so I'm going to explain relatively quickly how this can be done for Kyber. But first, I'm going to say a few words about high-order masking. So in high-order masking, as you know, we mask every variable with n. So we have n shares. So every variable x is shared among n shares x1 to xn. And so initially we generate n-1 random variables until n-1, and the last share is x, so x1 to xn-1. And so the goal is that if you only look at n-1 variables at a time, you learn nothing because every subset of n-1 variables is completely random and decorrelated from the secrets. And so we have theoretical results for high-order masking, and the basic result is the ISW paper, which showed that to get security against T probes, it's possible to get security against an adversary probing T wires in a circuit by using a countermeasure that is going to expand our circuit C into a circuit C prime of size C times T squared. So we have this penalty of T squared as the number of probes. And so there is a generic transformation of any Boolean circuit into a circuit that satisfies this property. So for XORs, this is easy because a XOR is linear. And for the AND, the multiplication, we have the ISW multiplication gadget. But actually, this is a generic transform, which is not very useful for lattice-based cryptography, because in lattice-based we combine arithmetic and Boolean operations. So of course we could apply this generic transformation, but it would be quite inefficient. So let me say quickly also a few words about the security model. So what we want actually is to have a proof of security, a proof that we are secure against an attack of order T or an attack with T probes. And the approach is based on simulation. So assume that, for example, so this means that, for example, for a block cipher, but it's the same for for a public algorithm, for the decryption of a public algorithm, we share the secret key into n shares. And we want to prove that if an adversary has T probes, then he learns nothing about the private key. So the adversary can probe wherever he wants inside the block cipher, but we want to prove that he will not learn anything about the secret. And so for this, the approach is based on simulation. So we show that we can always perfectly simulate any set of T probes from the knowledge of a subset of the private key. So we show that any subset of T probes can be perfectly simulated from at most n-1 shares of the secret key. But now we know that initially those n-1 shares, they are uniformly and independently distributed. So this means that this simulation does not provide this information does not provide the probes does not provide any information to the attacker, because the attacker could perform this simulation by himself. So he learns basically nothing. And so the argument is based on simulation. And but one may ask whether this probing model is really relevant in practice, because in practice, we don't have probes. We can perform a power attack in which we have a real-life leakage, which is quite different from a set of probes. So so here we have perfect probes, but here in practice we have real-life leakage, but which is noisy. But the advantage is that we have more information than only about T variables. But still, it makes sense to prove security in the T probing model, because this means that to perform a DPA or a statistical attack, if we want to recover information from the key, we will have to combine more than T points in the leakage. So at least T+1. So this means that if we have security against T probes, we must perform an attack of order T+1, which is going to be more complex. But one of the main lessons is in side channel security is to never publish a high order masking scheme without a proof of security, because so many things can go wrong. And actually, in the past, many countermeasures without proofs have been proposed and then broken because of this lack of security proof. And this is actually because we have a poor intuition of high order security. So there are so many ways, actually exponentially many ways of combining shares that there is no chance that a countermeasure is secure without a security proof. So let me describe how masking is done in Kyber, how we can protect Kyber against side channel attacks. So we can first see the first step, which is the decryption of C, of the ciphertext C, using the private key. So the private key is now shared among n shares, and it is shared. The private key is actually a polynomial over the ring modulo Q. So we can share the secret key S into n polynomials, but modulo Q. So this is called arithmetic masking. But at the end, what we want is the messages are bits, actually, or a binary polynomial. So every coefficient of the plain text is a bit. So this means that we are going to use Boolean masking. So where the message M will be eventually shared among n shares, n binary shares. And so the goal of high order masking is to compute this operation securely. So we are not allowed to recombine the S1 to Sn to perform this decryption, because in that case, the attacker could directly probe the recombination. So we must find a way of processing the shares S1 to Sn more or less independently, so that the attacker never gets information about the full private key. We split the computation into multiple parts, so that eventually we compute the shared value of the message M, but without computing M explicitly. So let me explain how this can be done for Kyber. So for Kyber decryption, you recall that N is the threshold function applied to this V minus ST times U, where the ciphertext is UV. So now if we assume that the secret key, the private key S is shared among N shares, modulo Q, it's easy that we see that this first operation is completely linear. So it's very easy to protect, because when we compute this scalar product, ST times U, we get the sum of the shares SI times U. And so this means that we can compute this first operation. We obtain can easily be shared, and we obtain a sum of shares W1 to Wn, where each Wi is computed independently from the private key. So this first step is easy. But what is more difficult is the second step, how to apply the threshold function. So we have the shares W1 to Wn, which come from the shares of the private key, but now, so which are defined modulo Q, and now we must apply the threshold function to recover the shares of these bits. But as I said previously, we cannot compute this sum explicitly, because in that case that will be insecure. We must compute this function in a shared way. So I'm going to explain how this can be done. So the question is how to higher order compute this function. So one observation is that if Q was a power of 2, so it's not the case in Kyber. In Kyber, Q is a prime. But if Q was a power of 2, then we see that this threshold function simply extracts the most significant bit. So this XOR M1 to Mn will be the most significant bit of this arithmetic sum. So this implies, of course, that we should use an arithmetic versus Boolean masking conversion. So what we do in that case, we would convert from arithmetic to Boolean masking. So we give as input the arithmetic shares, and we get as output the Boolean shares of the same value, and then we simply extract the most significant bit of every Boolean shares. So for M1 Mn, we can simply extract so M1 will be the most significant bit of X1 and so on. So in that case, it will be easy to apply this decryption function and to have security against high order attacks, simply using arithmetic versus Boolean masking conversions. And now I'm going to explain how to do this with Kyber when Q is not a power of 2, but a prime. But this is almost the same. But first, I'm going to recall the main Boolean versus arithmetic masking conversions. So when the goal is to convert between arithmetic masking modulo a power of 2, modulo 2 to k, into a Boolean masking. So the first conversion algorithms were described by Goubin more than 20 years ago in both directions. So the Boolean to arithmetic conversion is quite efficient. It takes only constant time, independent on the size of the modulus. And for arithmetic to Boolean, back to Boolean, the complexity is linear in the size of the register. And then this was extended to higher order complexity in both directions. And in that case, the complexity is n squared times k. And then there is also an algorithm in only the direction from Boolean to arithmetic, which has exponential complexity in the number of shares. So you could think that it's completely inefficient, but actually the complexity is independent from the size of the modulus. And in practice, for small values of n, this is much more efficient, at least 10 times more efficient for small values of n. So of course there are many more Boolean and arithmetic conversions, but these are the basic algorithms. So now how do we proceed when we have a prime Q? Because here in Kyber, the value is modulo Q. So in this paper, the technique was to apply a Boolean, an arithmetic to Boolean conversion modulo Q, because this conversion algorithm was described in this paper. And then one must apply some binary circuits. So we have 4 secure ANDs, and eventually it works. So and the complexity is n squared log Q. And a bit more recently, we described an alternative technique in which actually it's relatively easy to switch from arithmetic modulo Q to arithmetic modulo 2K. So this is what we did, and then we can apply a more standard arithmetic to Boolean conversion, and we obtain a slightly better complexity, at least for small values of n. And yeah, so let me say a few words about the remaining of the higher order masking of Kyber. So we want to also to mask the re-encryption of Kyber. So within Kyber, so we must re-encrypt the message, and so we have a message which is shared among Boolean shares, and eventually we must obtain a re-encrypted ciphertext which is defined modulo Q. So we must also convert from Boolean to arithmetic, and for this there is a very nice algorithm from this paper which can do this very efficiently in complexity n squared when we start from 1 bit Boolean to arithmetic modulo Q. So that's for masking the Kyber re-encryption, and we must also mask the polynomial comparison, as I said. And so and in this paper we describe some hybrid approach in which for some coefficients we use compressed coefficients, and for some other coefficients we perform the comparison with uncompressed comparison, and complexity still n squared. So that's for the masking of Kyber. And so eventually we obtain this kind of timings in which so we see that we have a huge penalty, because to get, for example, second order security, we get a penalty factor of roughly 20 between compared to an unmasked implementation. And so I think I don't have time to to describe dilithium. So I will jump. Maybe I can jump quickly to the performance. So yeah, so here I explain for dilithium. So there are, of course, such an attacks, and so here that's for the performances. So we have also implemented higher order masking for dilithium. And what I wanted to say, what is in, so and still we have a huge performance penalty, factor 100 compared to unmasked implementation. And what I wanted to say is that what is interesting is that, so for unmasked implementation, normally the polynomial multiplication, the entity is slow. It has been optimized. But on the other hand, when this is a linear operation, so which means that it becomes very fast compared to the rest for when we apply the such-channel countermeasure. And conversely, there are some very fast operations like the rejection sampling and the decompose, which are straightforward when you are unmasked, but which become very costly when you want to apply higher order masking. And so conclusion, so the field of post-quantum crypto is interesting from a side channel point of view, because there is a variety of algorithms and of techniques. So it's in generally more interesting than for only block ciphers in which we have only Boolean operations. And so what are the challenges? We want to still minimize the complexity penalty for countermeasures, which is still very, very high. And one possible approach is to design from the start schemes which are side channel friendly. And so for example, there is this interesting raccoon signature submission, which is completely side channel friendly. So thank you for your attention.
We can take some time for a few questions, quick questions.
Thanks for the talk. Given the large overheads, would you recommend keeping circuit level masking techniques, or would you recommend switching to lookup table based masking techniques? Is there any part where one may win over the other across all the spectrum?
Yeah, so for masking, we also know side channel masking techniques which are based on lookup table, and this also includes the conversions between Boolean arithmetic masking. You can do this based on lookup tables, and for the performances, it depends actually. So for some countermeasures, you get some improvement, and for some others it's less efficient. So it really depends. So for example, if you look at here, what we did. So this last conversion, when we implemented it, it was based on lookup tables. But on the other hand, there are some countermeasures in which it's better to not use lookup tables. And so it depends also on the target and the implementation technique. For example, if you want to do bit slice, so bit slicing is not very compatible with lookup tables, but with bit slicing you can get a huge performance boost. So it really depends.
Yeah, two questions, because I really like the slide where you mentioned how the cost of like higher order masking increases in the cycle. I was just wondering, now if we compare, let's say, an static key to an ephemeral key setting, so the load of like side channel countermeasures can be reduced over there, but then we have to do the key generation every time. So which is more expensive, like the key generation or higher order masking? Like if, let's say, as a designer, you have to make a choice.
Yeah, in principle, you also have to protect your key generation against side channel attacks. And so it might not be so efficient to generate new keys every time. So that's maybe I did not understand your question.
Like if you are in an ephemeral setting, then maybe like the masking requirement can be reduced. We don't need a very high order masking, and but then can we compensate? Like is the timing reasonable so that we can do an ephemeral setting, which means we can let's say always generate the key, and is it less expensive than, for example, doing the higher order masking?
Yeah, I think it really depends on the scheme. We did this exercise of masking the untrue key generation, but only for untrue, and it was very costly. So it really depends on the scheme. Yeah, I think.
So the reject there is for like when you check the norms of Z. That's for that.
Yes. Well, this is the rejection. Yes, this is the rejection sampling in which we test the. This is basically this operation. So the value of Z is masked, and we must perform this rejection sampling on masked polynomial, because if you cannot recombine the shares of Z and then perform the rejection sampling, because in that case the attacker will know some polynomial Z which would have failed the rejection sampling, and then the attacker can perform a standard statistical attack.
Then, like on the table, also you also have a paper when you get kind of split up there, and we get the conclusion that something Y was very costly, while in the table it looks like it's not that costly compared to the rest. So I was wondering whether this includes the K track that you need to generate Y.
The K track. So for Y, what we do is we simply generate uniform and small uniforms. So we don't use K track actually here for generating Y. We use the the probabilistic approach in which we generate these coefficients in a shared way. And also we use also this very efficient Boolean to arithmetic conversion, which is very fast for small values of n. So that's why I guess it's not so costly for small values of n, but for higher security orders, it could be much more costly.
Okay, then let's thank the speaker.
Hi everyone, welcome to this PhD forum that will be in 2 parts. First part is lightning talks during 7 minutes for each participant, and no question will be allowed, but you will have plenty of time to discuss with each participant during the poster session afterwards. And we will quickly start with the first participant, which is Anders.
Okay, thank you for the introduction. Good morning, everybody. So today I have this pleasure to be the first one in these lightning talks, and I'll be presenting you my PhD work that is titled Implementations of Post-Quantum Cryptography Algorithms Secured Against Physical Attacks, and directed by Damien Vergniaud and Alexandre Berzati. But first, a little bit of context. So thanks to the nice talk from this morning, if this works or... No? Okay. Maybe now? Yeah, okay. So I won't have to say all those things again, but so there's this quantum algorithm, Shor's algorithm, that can solve the integer factorization and discrete logarithm problem in polynomial time. And so this is bad news for RSA and ECC. And basically, the National Institute of Standards and Technology said in 2017, hey guys, we should have a competition in order to find new crypto systems, public key crypto systems resistant to quantum computers. And so now we are in a position where we have this first draft. So one for key exchange mechanisms, Kyber, which is based on lattices, and 3 signature algorithms. So 2 of them are based on lattices, Dilithium and Falcon, and 1 is based on hash functions, Sphinx Plus. And so now we have also a 4th round of competition to find new signatures algorithms that are not based on lattice problems, in case, well, these problems are easier than we thought they were. And so we have more algorithms based on multivariate polynomials or other principles such as MPC in the head. Well, and just to make a brief recap from yesterday and the block ciphers, so we also have these Chinese algorithms, the ones from the Korean competition, post-quantum competition. So all these algorithms will need to be implemented securely and efficiently in a variety of use cases. And so this is basically the context of my PhD. So I started back in May 2022, and if everything goes well, I should end in May 2025. And so it's a PhD, an industrial PhD between the Almasty team in the Lipsis laboratory at Sorbonne University and Thales DIS. And so basically, when we first started by looking at some post-quantum cryptographic algorithms, and we were hoping to find some of them that were the most interesting. So we basically went with a bundle of algorithms. So it was Kyber and Dilithium, which were the most promising at the time. And so it's nice because now they are being standardized. And so the idea was to study them in order to implement them securely. And so, well, by doing this, we had a first problem because this new type of post-quantum cryptographic algorithms have first very large key size compared to traditional algorithms. And so if we did this, and if we added security on top of that, we added too much of an overhead for embedded systems. And so we changed our plans a bit. And we decided first to try and optimize the schemes. And so mostly Dilithium, because it's the one that takes most space. And then after, with this optimized implementation, we decided to study all the attacks from the state of the art and try to find new ones. And especially in Dilithium, because there are already too much attacks on Kyber, but not only on the standard implementation, but also on the mask ones at the 1st, 2nd, 3rd, 4th, 5th order mask implementations. And so with this insight on attacks and countermeasures, we could implement them securely. And with this strategy, we should have an efficient, optimized implementation of the schemes. And so for the first part, the optimization part, here, the problem with Dilithium is that, for example, if we take the Dilithium 5 security level, so here, if we take the public matrix A, it has 9 times 8 times 250 coefficients that fits in 32 bits. And so just for the public matrix, which is a lot. And so the goal was to reduce the RAM consumption from the signature algorithm. And if we implement these schemes just as it is, we can see that the RAM consumption for the security level 5 can reach up to 100 kilobytes. So this is quite a lot. And we had an implementation that fitted already on almost 50 kilobytes. And so the goal was to reduce this RAM consumption up to 30%. And so we managed to do this. And at the end, we have an implementation that is conform to Dilithium and so MLDSA as well. And that fits almost under 30 kilobytes for all the versions. And so then we wanted to see if there were other attacks possible. And so we found one on the signature algorithm of Dilithium that exploits a zero value leakage on some value during the signature generation. And so we showed that this indeed allowed to recover a part of the secret key that in turn allows to forge signatures. And so in our paper, this confirms the need to protect this intermediate value. And we have also shown a practical demonstration with a template attack. So this was published at CHEST, and we presented this work back in September. And we are still planning on releasing the artifact that goes with it, so the code. So stay tuned for that. And so just to recap, yesterday, we did also a sensitivity analysis on the verification algorithm. So basically here we show that you have to make sure that the vector C times T1 times 2 to the power of D is not smaller than it needs to be. Otherwise, false signatures can be accepted through the use of port attacks. And lastly, so now for future work, we are still planning on identifying new attacks on Kyber and Dilithium and the new algorithms of the round number 4. And also to keep studying all the countermeasures that are available, and particularly a novel way in order to implement the decomposed function securely. And we are also planning on studying novel ways in which we can implement Dilithium in Kyber, such as to combine efficiency and security. So if you are interested in any of these topics, or if you have any questions, please come see me at the poster session. And thank you very much.
Thank you, Anderson. Next speaker is Azad.
Hi, everyone. So I am Azad, and I'm going to talk about attacking pair-point-wise multiplication of crystal Kyber using deep learning. So thanks to all the gentle introduction and talks today and yesterday, I think that I can skip the introduction. Maybe just a simple reminding that Kyber is a key exchange mechanism. And maybe a quick wrap up about lattice. So here in lattices, we have two basic, actually, this is a very high level simplified example of lattice, but you see two vectors here. Adding these two vectors, we can go to a new point. And if we add these two vectors with different, multiply of these vectors, we can have a space of many points that can simply build using this basic matrix, basis vectors, and multiplier. This is a very high, let's say, introduction to learning with error problem. So if we have this point here, this is very easy to having A and having the result of multiplication find S. But if we add a very small error vector to it, then it is a computationally infeasible problem for both classic and post-quantum computer. And here you can guess easily that A and T are the public key and S is the secret key. And this E here is the error vector that we add to the result in the end. And here, maybe just two things that I should mention is that for the Kyber implementation, all the matrix and vectors have entries of a polynomial, and the polynomial is in this ring, which simply means that all the degrees of polynomial is less than 256, and actually Q is 3,329. There is a typo here. We need lots of multiplication in Kyber, and to somehow reduce the time that we need for multiplication, we do this multiplication in entity domain. Entity is simply a kind of Fourier transform, and when we transfer a polynomial in entity domain, then it is, in case of Kyber, because of the ring and everything that is there, so the polynomial can be simply shown as 128 sequence of other polynomials with degree 1. So here you see an example. Now imagine that we have two sentences that we want to multiply them together, A and B. A can be, for example, the secret key, and B can be the cipher. You need simply first to transfer these two polynomials to entity domain. Then with this pair point-wise multiplication, you can calculate all the coefficients in the entity domain. Here you see this pair point-wise. And then finally, when you have 128 polynomials in entity domain, you can do the entity invert to go back. Now you know everything to attack the pair point-wise multiplication in Kyber. Here you see the secret key in polynomial domain is multiplying with the ciphertext in entity domain. So this is a vector. Let's say it is a vector with dimension 3. To multiply the first sentence with the ciphertext in entity domain, yeah, you just need to repeat this assembly code 64 times. These blue lines that you see here are actually that pair point-wise multiplication that you see in the other slide. And we believe that because here we are multiplying a constant with this poly1, which includes the secret key coefficients, and here we are multiplying the poly1 with poly0, which includes the known coefficients of ciphertext. We can easily recover the coefficients of secret key using deep learning. And this is the model that we are using. What we are doing here is to, maybe I can go back. So here this poly1 and poly0 are registers with 32 bits, and each register, for example, poly1 includes 2 coefficients. And because it includes coefficients smaller than Q, so it only each coefficient only occupy 12 bits. So here we recover 2 coefficients together at the same time, bit by bit. The first 12 byte is for the first coefficient, and the second 12 byte is the second coefficient of that pair point-wise multiplication you have seen there. These are 24 separate deep learning model, MLP actually, and on the top we have a 2-layer CNN convolutional network to extract point of interest. And this is the result we have already for the attacking this point. Actually, you see that we couldn't find the actual coefficient. It somehow stops and doesn't go smaller than 500. And we believe that we can improve the result maybe by searching for a better model, or by increasing the number of points, because now we are using chip piece better and we do not have enough samples. Maybe we can simply use some other thing to increase the number of samples. Thank you for attention. Yeah.
Thanks for that. Next talk is from Wang Winyan Fa.
Thank you. Good morning, everyone. So it's a break from on-site genotypes. So I'm a first-year PhD student at Boone Trustway Evident and University Grenoble-Alpes in France. And I'm going to talk about part of my PhD subject, which is only the efficient implementation of Kyber and possibly Dilithium after, but just Kyber for now on RISC-V. And today we're going through some modular multiplications and our implementation of Kyber RISC-V and some current results and future work for my thesis. And so the Site-Montgomery multiplication you are very familiar with that have been used in Kyber and Dilithium. And so for Montgomery multiplication, we have three little multiplication here, three little multiplications. And we have a dedicated representation called the Montgomery representation. And the inverse of Q is modulo 2 to the n. And so in 2021, Thomas Blanchard has introduced another multiplication. I must say that it's an inheritance of the Site-Montgomery multiplication, even though this Blanchard multiplication is unsigned. And in this multiplication, even though we see that there are three multiplications too, but right here, this is the important thing, is that by pre-computing the multiplication between B and the constant R, we can reduce it to only two multiplications. And we think that this might come as an advantage in the context of Kyber. So that's why we want to see whether it will work better than the Site-Montgomery or not. And we see that there is also a representation, and to which I refer as the Blanchard representation. And we see that the inverse of Q is mod 2 to the 2n. So the constant is double. So that's in the context of Kyber, when we multiply the roots of unity with this constant, so it will be the array of 32-bit integers instead of 16-bit integers. And so our implementation of Kyber RISC-V is inspired by the paper Britzman, Siegel, and Sepulveda, which is RISC-V is a set of tightly coupled RISC-V accelerators for post-quantum cryptography. And in this paper, they were targeting, especially New Hope and Kyber and Sabre were coming just as a second options. And among several new instructions that they added, there are 5 instructions that we are particularly interested in. One for the modular addition, the other for subtraction, multiplication, one for single cycle Cooley 2-key butterfly, and other one for gentleman sand butterfly. And there is 5 instructions for binomial sampling, whose only one is only for Kyber route 2. At that time, it was eta equals 2. And the work was done on the Pocono system on chip, whose core is the single issue for stage 32-bit RISC-V, written totally in system Verilog. So the target is to modify all these instructions with ordinary instructions, and the multiplier will be the Blanchard multiplication. And so for the Blanchard multiplication, later 2021, I think, there is this paper by Huang and An. They have improved the Blanchard, and this is a side version of Blanchard multiplication. And the interesting thing is that they have widened the input range and shrinked the output range into just Q minus Q over 2 to Q over 2. And this enables the lazy reduction. We don't have to reduce the coefficients before entering the base mode. So for some pair-point-wise attack against unprotected Kyber, this lazy reduction comes in very handy. And the last one, there are some 2 techniques that we have taken from faster Kyber on Cortex M4 of Abdurrahman Huang, Ken Wisher, and Sprinkles, and we will use the Cooley 2-key butterfly for both entity and inverse entity with the set of floating point registers, and we will merge layers of entity and inverse entity with a ratio 4:3 instead of 3:1 like in previous works. So by combining all the previous approaches, I've introduced 3 instructions just for Cooley 2-key butterfly. One using the twiddle vector from general purpose register, one directly from the floating point register, and one just for the light butterfly, in which the twiddle vector is 1. So this can considered to be the modular, vectorized modular addition. and one for the modular multiplication using the Blanchard multiplication, and one for to help the basement function, two other instructions that we can do binomial sampling for eta equals 2 and eta equals 3 for Kyber. And for the assembly code, we used the techniques from faster Kyber, Dilithium and Cortex M4 for RISC-V. So this is only for Kyber and I must say unprotected. And we compare our work to the original result of Fritzman in 2020. And for example, in Kyber 512, for Keeper, we have obtained 72,000 cycles compared to 150,000 cycles in original work, and we have gained 52%. And for encapsulation, 47%, and for decapsulation, 42%. And we have also compared the results with the unprotected Kyber on a loosely coupled entity accelerator, written also by Fritzman and in 2021, but for masked implementation, and we have gained for like 40% in general. And it works best for Kyber 768 because our specific approach for Blanchard multiplication. So I think this is a good sign when you use the Blanchard multiplication. And so as a future work, we want to implement Dilithium with Blanchard reduction, but due to the nature of Blanchard, it will be on 64-bit RISC-V instead of 32-bit RISC-V and some masked Kyber and Lithium on RISC-V. That concludes my presentation. Thank you so much for your attention.
Thanks a lot. Next speaker is Jérémy.
Thank you. So, hello everyone. So, since yesterday, my name is still Jérémy Guillaume. I am in a third year of PhD, and the subject of my PhD is the screaming gate array study and characterization of IP data leakages in mixed signal FPGA system on chip. To make it simple, it consists of studying a specific case of such channel attack on mixed signal and reconfigurable devices. So the specific case of such channel attack, I already presented it yesterday, but just to remind you what it is a screaming channel attack. So it's a such channel attack on mixed signal where we have a radio frequency module which is going to involuntarily transmit the leakage at a distance. And this attack has been demonstrated in 2018 by Giovanni Camorati, and they demonstrated it on IoT devices. And what we wanted to do in my PhD is to study this attack on devices that are mixed signal, but also reconfigurable. So we want to trace the attack on the RFSoC, which is a system on chip from Xilinx. It integrates processing system, programmable logic, and radio frequency interfaces. And this device is designed for telecommunication and radar application. But before to reproduce the attack on this device, first, I had to reproduce and handle the initial the screaming channel attack. And from there, we had some contribution. The first one being about trace synchronization, because when you perform a screaming channel attack, you want to be at a distance from the victim. So you do not want to link the victim and the attacker by a wire to transmit a trigger signal to indicate the start of the encryption. So what they did in the previous work on screaming channel attack, they used a frequency trigger mechanism. It consists in finding in the output of the radio frequency spectrum of the victim, finding a frequency component at which we have a signal that acts as a trigger signal, meaning that each start the cryptographic process, so here it is the AES, each time we start the AES, this signal is going to change of value. And if we detect here, for example, the rising edge, we can use this signal as a trigger signal. So this method allows to remove the need of a trigger signal, but it has some limitation. For example, we cannot guarantee that on all the devices that we want to attack, we'll have such a frequency component that act as a trigger signal. And also, it can be very sensitive. We have some parameters that can be unstable and make this method difficult to reproduce. So we propose another method which reduces the complexity for trace synchronization, which was the virtual trigger. And in this method, what we do is we find the precise time duration of one cryptographic process. And once in the papers that we submitted last year at CIPS in 2022, we explain how we do to find this precise length. And once we have this length, we just have to segment the raw trace from the victim in segment having this length. and we get multiple segments that each segment corresponds to the leakage of one cryptographic process. And if we average them, we get a trace with reduced noise, and then we use this trace as a pattern to do pattern recognition, and it works perfectly well in the context of screaming channel attack to collect synchronous traces. After that, we wanted to ask another question on the context of screaming channel attacks, which was about frequency diversity, because in this attack, the leakage is transmitted at multiple frequency, multiple harmonics. And in all the previous work on screaming channel attacks, they collected the leakage at only one harmonic. And the question we had was, what happens if we collect the leakage at multiple harmonic and we try to combine them to try to improve the attack? So we did an experiment where we collected the leakage at the 4 first harmonics, but in our environment, only one was good enough to success the attack. So we did not have frequency diversity. And from there came all the work that I presented in the talk yesterday, where we demonstrate that we can use all the frequencies and the harmonic to success the attack. And after this, we came back to our initial question, which is, if we have multiple frequencies where the leakage is present, can we try to combine them to improve the attack? So we perform the attack at 150 frequencies, and we order them from the best one to the worst one, and we voluntarily reduce the number of traces used at each attack, around 100 traces, to make the best frequency not good enough. Here, the key rank is 2 power 50, so I don't even know how many times we will need to brute force the key. And what we do is we took the best frequency and we combine it with all the other. And here is what we get. So the first one corresponds to the combination of the best frequency with itself. So of course we don't know to prove anything. But here, when you combine it with the second best one, we reduce the key rank. It is still high, but we reduce it. Then we took the best combination and we combine it with the initial trace, and we reduce again. And we did this until 5 combinations. And we can see that we came from a situation where we can consider that the key is unbrute forceable, at least the brute force complexity is too high, to a situation where we could brute force the key in around 1 hour, less than 1 day at least. And now we are trying to find new method to understand how we could use the weak frequency, meaning the frequencies that even when we combine them with the best ones, they only reduce the attack. And that's all, and I look forward to discuss with it around the poster. Thank you.
Thanks. And last but not least, the last talk will be given by Abolfaz.
Good day, everyone. My name is Abolfaz Sajati, a PhD student at Leiden University. And today I'm excited to share with you the progress of my PhD project. My PhD project, PROACT project, and in hardware aspect. PROACT is a collaborative project including Leiden University, Radboud University, and RISC-V. And the project's goals is to increase physical security strengths of cryptographic algorithms, and thereby increasing the probability of the first-time right cryptographic hardware implementation. And by this approach, we aims to reduce time to market and improve design quality. And how can we achieve this? By developing and validating a pre-silicon leakage analysis tools or a simulator. To do that, we analyze various leakages in some components, and with a special experimental platform which will be implemented on ASIC chip to help us do power sidechain analysis. Our experimental platform enables comprehensive leakage analysis across various components. This includes analyze leakages for the software running on RISC-V or coprocessors or RISC-V ISA extension. Additionally, we assess leakages after implementing some countermeasures. And also we have a controller to manage all components here. This slide shows the schematic of our experimental platforms. And we have a software RISC-V target here. And we have multiple coprocessors. And control is managed through two 32-bit register as a control register and a status register. We utilize IBEX core for both controller and software target. IBEX is a open source 32-bit RISC-V core. It's recognized for being one of the straightforward and low power RISC-V processor available, and it has two-stage pipelines. For program and controller, we employ SPI protocol interface, and in our design we have a SPI bridge to enable us accurately write instructions and data to their intended addresses. And by do this, we can add flexibility to our design. After control program is loaded, controller initiate communication by user through the UART interface, and user can send some commands like reading, writing, or even active or disable any coprocessor or processors. Before moving to manufacture as a real ASIC chips, for ensure everything correctly works, we utilize of a FPGA port. It's a pin port contain a zinc chip, and for our purposes, we just use of FPGA part of it. And also for simplify user interface, we have developed a nice graphical user interface with PQ.V.ALU.E that enables us to control reset signals or monitor it, and manage all drivers, communication with SPI and UART. Additionally, we can read a status register, write control register, or read or write from specific addresses. And for the future work, we have planned to integrate more crypto cores like Zodiac AES and collect real traces from the chip and analyze and do power side channel analysis to develop a pre-silicon leakage analysis tools. And we will do ASIC follow in parallel. If you find if you found this presentation is interesting, I'm here for more detail. Thank you for your attention.
Thank you. So let's start the third session about smart card and efficient implementation. The first talk will be the adoption rate of JavaCard features by certified products and open source projects. A job performed by Luca Zawal, Antonin Dufka, and Peter Swida, and Peter will present you the paper.
Thank you very much. Good, so welcome here. My name is Peter. I'd just like to ask how many of you know what JavaCard specification is? Raise your hand. Okay, few people. Leave your hand up if you program something, at least small JavaCard applet. Okay, good. So we have some understanding. I will anyway tell you. So I'm the last author. I'm the oldest one. The guys did most of the work, but they were afraid that the questions will be more like philosophical about the long-term evolution of this ecosystem. So they said, okay, you are better to answer this because you are doing this a long time. Okay, so let's start. Okay, does it work?
Click in there.
No,
You should probably click in the screen and then it should.
okay, somewhere on the screen. Work. Okay, now it works. Okay, so the JavaCard specification was born out of need to have environment which allows portability between the different cards. Because back in the days, different card, different API applications not portable. So telecom operators like pushed to have the SIM cards applets portable between the cards. And Sun, together with Schlumberger and others, basically built the initial version of JavaCard specification. Java is not known to be particularly fast, right? But so maybe this like sounds like a strange choice for a very small and not performant device like smart card. But the portability was good. And also, given the fact that you need cryptographic algorithms that need some hardware acceleration anyway, you are not writing the crypto in a JavaCard bytecode. You're using the accelerators to do most of the work. And in the applet itself, you are just like taking the data, sending it out, preparing for coprocessor. So there is a specification since 1997. There's also a graph, 20 years of JavaCard evolution from last year. You can see that there are many different versions of the specification that happened over the time. What is important to understand is that you can't update cards usually. So if you are buying some card which is produced with specification 3.0, you're stuck with that. Okay, it can't be like you can't just upload additional new version when it's up. Okay, so you're stuck with that. Also, there are mandatory and optional parts, which makes sense because you don't like to force vendors to implement everything. But the problem is then, of course, they are not implementing some parts. Okay, so you just because you are implementing this specific version of specification doesn't mean that you are implementing all the algorithms that are there. Okay, so that's one potential problem. But you are getting the applet portability, so you can really compile once and then just send it to different cards, except when you will start to be dependent on algorithms that are not supported on other cards, because either they're optional or they are not in a public API, they are in proprietary packages. So customer, like vendor lock-in is still also an issue. So this graph is almost, or this picture is almost complete. We have since January this year, the newest 3.2 specification, which is adding some Edward Curves DSA and TLS 1.3 support and so on. And the question we were, two more things. One, this suggests to be number of cards. This is somehow plateauing. Like this suggests to be still rising, which is not really true. Like we are around 10 billion pieces per year sold. 2002 is time when I first went into this domain and saw the first applet, and I was confused why there is no main functionality. And since then, I fell in love with smart cards. I'm collecting smart cards. I'm trying to do open source development around that. So our question was, how much is the specification followed in practice? What is, okay, something is written in this specification, many algorithms. To what extent the cards are supporting it, and to what extent applets using the cards are demanding it or using it. Okay, so that's the research question we have. If you like to analyze some technology, what is the usage? So you are basically doing three things. You need to have a representative samples of users' projects, ideally all of them. Okay. Then you need to somehow say what is garbage and what is just like some plaything and what is important project. And then you are then analyzing these projects, what they are actually using. In our case, it would be like what algorithms they are using. So if we will apply this to JavaCard, all projects means especially all proprietary applets, because this is where most of the JavaCard developers are working, not in open source, but in a say proprietary applet world. But we don't have access to this. Okay, if you are working on a proprietary applets and you would like to share some results with me, I'm one eager. So what we did instead, we collected all the open source applets we were aware of. So more than 200 applets. They are publicly available. If you know some more, just please open a PR. Significance of projects, different metrics, number of developers, forks, stars, Google Trends. You can also look what the vendors are willing to pay for, because if they are going to the pain of certification, paying a lot of money, waiting a lot of time, like they likely think it makes sense. And then with analysis, you can do static dynamic analysis, how what are the algorithms and constants used by the code. You can also run it on the real cards to get understanding of the memory consumption and stuff like that. Ideally, you would like to get also the trends in time. And with the open source applets and thanks to Git, we can do it, right? We can just look what was the situation in the year 2015, okay, in December, let's say. So this is what we did. So let's start with the statistics we can get from certification documents. So common criteria and FIPS 140 are the main one here. And these are likely the most detailed information you can get without signing non-disclosure agreement. Okay, so if you are not looking at these, definitely do, because there are a lot of interesting things. And you can write a bunch of regexes, regular expressions that will match things of your interest. So for example, we can try to match what is the version of JavaCard used and specified in that particular certificate, or what algorithms are exposed by that card that is certified. Okay, so this is what we did here, and this is the result. What you can see here is a evolution in time, starting in 2000 and then going up to today. And these are all certificates, common criteria and FIPS 140, that are somehow referencing some version of JavaCard specification. Okay, so this is what you see, different colors, different versions. These are not just smart cards. This can be also applets like signing applet or electronic passport applet using some physical smart card. So also you can have certificates just for that applet. For the cards, between 2000 and 2009, the certificates were just for just within FIPS 140, and then it completely switched, and now it's just common criteria. Okay, so we matched all the versions. And so what we can see out of it, year 2023 is only till last week, but it seems that this will be the best year ever. Okay, so we are still getting more and more certified devices. So at least within the certification ecosystem, this is not dying. What we can also see is we have no 3.2 version of the specification certified yet. You can see that the specification was released here, but no 3.2 card or applet is available yet. Usually there is like delay 1 to 2 years after the specification released and the first certification is published. Good, but you can look deeper. You can look at the algorithms. So I just kept the graph for your reference to see the complete numbers. If you will look here, these are the algorithms introduced by specific version. I started from version 3.0.1. So all these like AES with the various block sizes and so on. And this is a heat map showing in particular year, okay, this is closer to where we are now, how many certificates were referencing this specific algorithm, okay? So we did that for various versions. So you can see that, like this is 3.0, this is 3.04, this is 3.1.0, okay? So what you can see here, how to interpret this. So first of all, you have these like bands. So these bands are basically telling you in that particular year, more certificates were referencing a lot of these algorithms. And you can see that this is heating up. So we are getting more and more certificates. I suspect also that basically vendors are listing now more these algorithms in documents. So we can get that. Okay, so this is one band. Another band is like this direction. This is the particular one algorithm. In this case, it's CDSA with SH224 below it. The reason why it's there is likely that this is like somewhat specific SH2 version. So vendors like feel that they need to list it explicitly. Okay, so this is my explanation. Also, the interesting spots are this one and also this one, which is actually Diffie-Hellman with plain output with both X and Y coordinates of the point. Do you have any guess why this one might be of interest for the people, both for, say, proprietary developers as well as open source developers? Go ahead. Yes, yes, because if you will look at these algorithms, they are mostly like sign something with RSA, use SH1 as a hash function, and then you will get the signature. And you can't do much about the process. You are just preparing the data and you're getting the signature. What if you like to implement your new fancy algorithm that requires EC-point scalar multiplication? Then you are out of luck, or you need to sign non-disclosure agreement and get access to proprietary packages. But with this algorithm, which is Diffie-Hellman, you can get that functionality basically, because it's what basically it's doing. Also, there is a base implementation that was used in passports. You can get also addition. So you can start to see algorithms that are very helpful to build something that was otherwise not available in an open API. Good. But we have a limitation here. If the vendor decides, I will not mention particular algorithm in a certification document, then we don't see it. So we need to go deeper and see what's there. Okay, so how we can go deeper? One option is to analyze the real cards. So what we can do is, and we did it with our JC Altes project since 2007, we were taking the cards, implementing applet that tries to create the instantiation of all algorithms that are available in or specified in a JavaCard specification. And if successful, great, we know card supports it. If not, then we know it's not supported. Right now, there are more than 100 cards, half of contributed by community. Thank you very much for that. And you can then do drafts. If you are interested, we have the paper describing the details, but there is a big limitation. Again, we are reaching the fact that we can't analyze the newest cards, right? So for example, in this open database, the newest card is Jacob 4 on P71 from NXP. Yet already Jacob 8 on like free versions, better processor is certified and available to large customers. So we are like lacking behind with the analysis, unfortunately. And I think this is like damaging for the whole ecosystem. So, okay, we can still go deeper. We can take the applets and analyze how the applets are actually using the cryptographic functions, when, what parameters, key lengths, and so on. So we have the database, more than 200 applets. If you will go to GitHub, you will see that. There are not only applets, there are other things, but that's what we are interested in. We can also see how many contributors when they were active and so on. And because it's a Git, we can also monitor evolution in time. if you will have something, please contribute. We also built a tool that allows us to do static and dynamic analysis. So we can first of all, it's based on Spoon from INRIA. We can get all the algorithms, all the methods, all the packages that the particular applet is using. That's one thing, static one. And we can also instrument applet with additional code, which allows us to monitor memory consumption and stuff like that. We tested on a simulated card. JCard Sim is open source simulator. The simulator is having no limitations of the real hardware. So what you are mostly getting is if the applet is, I don't know if you can see that, but if the applet is basically, if you can even compile it and in theory run on the card with no limitations. So out of these 200 plus applets, we were able to get, you can't see the number, but after some minor fixes, 187 applets. And if we will just follow all the steps you need to get the applet to virtualized card, we are ending up with 144 applets. So this is our base on which we are then doing all the analysis. Still decent number, so I think that's good. We are also testing on the real cards. We are using these three to get the idea about the memory consumption and also about the portability between the different cards, because JavaCard was supposed to be portable. You can see that overall, Jacob 4 is the one where we can upload most of the applets. Out of 144, 124, we can upload there. And then the different cards, different number of open source applets can be uploaded. Why? Usually because it will fail in install command. An install command is the time when you are allocating in constructor resources you need. And you are asking, hey card, please give me IS engine, or hey card, give me Diffie-Hellman engine. And if it's not there, it will fail. Okay, so you see the difference. So let's take a look at the popularity. So we took all the applets. This is the number of forks on GitHub. This is the number of stars on GitHub. So you get some idea what's popular overall in open source ecosystem. And you can see that most of the projects are not that popular, right? They're all here. Not many people fork it. Not many people like it. So what, just for comparison, like OpenSSL, again, you can't see it, but they have more than 10,000 forks and 23,000 likes. Or NFC card reader, some Android application, there are like 500 forks. So just give you a sense of difference. Like the thing in JavaCard open source world is not that much popular, right? We are talking here about like 70 at maximum. So what applets are there for these more popular ones? The green ones are identity applets. So usually something like PIF standard implemented on card, FIPS 201, and stuff like that. Okay. Then PGP applets supporting signature and encryption. That's there as well. Ubico Open PGP applet is the most popular one. And then Bitcoin related things. So open wallets you can upload on your card. Okay, another question you can answer is we have these JavaCard specifications specifying a large number of different algorithms, key lengths. In total, it's 583 constants. So how many of them are actually used by open source applets? And you will realize that most of them are not. That 404, nice number, they are not used even single once by open source applets. Okay, so it's almost 70%, completely unused. Only 42 constants, again, nice number, is used by more than 25 projects. So very small part of the specification is actually utilized by open source developers. And the rest is somewhere in the middle. The popularity may change over the time. We can analyze it because of the Git. So let's take a look at some examples. So we have the popularity of applets, open source, basically whole open source ecosystem in time. And what you can see here, the blue ones, this is per month, and the red one is aggregated per year. And what you are seeing is the number of active projects in that particular month or that particular year, based on GitHub comments. So you can see that, okay, it was quite active here. Any guess why it started to be active around 2013? So say it again.
Bitcoin wallets?
Bitcoin wallets, okay, that might be, they are part of that. But especially if you like to do open source applet, you need to have a card, right? And till 2010, it was very hard to get cards on the open market. But finally, we have it. Okay. Okay. This is since the mid of the year. We checked whether it changed after the paper submission, and it changed by 1. So it seems that the whole ecosystem is declining. Okay, so we had the peak around 2017, but now it's declined. We can also analyze all the algorithms, how they were used in time. So we have a large number of graphs like that. You can download that, but I will not bore with all of you. I will just highlight some examples. For example, you can take a look, what is the difference between the adoption of RSA signing algorithm and ECDSA-based signing algorithm. And you can see that the RSA, the light green, is the new edition of the code that is like newly adding support for RSA. And you can see not much. Whereas for ECDSA, still applets are adding support for that. You can also look at the key lengths. So this is for TripleDES. Still, TripleDES is something that people use, and you can see over the time that they tend to use longer and longer keys. I'm almost done now. So we are now looking at the memory resources. This requires dynamic analysis. You need to instrument the applets. And we did it on these 3 cards. There were only small variations among them. So basically the question is, it's well known that the smart cards are having limited memory. Is this a real issue for open source cards, open source applets? And the answer is not that much. For persistent memory, most of them will fit under 10K. For transient memory, which is even more limited, most of them will fit under 1K. Okay, but the question is, what is like reason and what is the effect? Because maybe they are forced to fit within the small memory because there is not much more memory available. And we know some applets that can't even fit on our cards, that requires way more RAM. And the reason is typically they are trying to do something that allows you to get an easy point operation exposed and then do some interesting stuff on top of that. So there are some exceptions. Overall limitations, it's open source ecosystem, not proprietary ecosystem. So I would love to test proprietary applets, but this is not available. Second thing is new cards, like the very new cards are not tested. So if you can share with us new cards, great, please do so. And also we are testing only up to select method, but in general, this shall not be a problem because of the, let's say, good programming practices here. So the conclusions, with respect to cards manufactured and support for JavaCard specification, likely this year will be the best one overall. Large majority of JavaCard constants are unused. So most of them are unused, at least for the open source ecosystem. Open source ecosystem peaked and now is declining. And we have hard data for that, but we can then discuss whether it matters, whether it's bad for the overall industry or not. I think it is, because it's the fact that the open source ecosystem is not having new cards and not having access to the operations that are necessary for nice and let's say new, fresh implementations. This is harming overall development in the domain because the big vendors will do banking applications, telco, and maybe some government identity applets, but they will not try like interesting new niche things. So I think a lack of new ideas that would otherwise come from open source ecosystem, we are missing that. Important part is analysis of proprietary applets, which is missing, but I don't know how to do it without the proprietary applets. And all tools are available if you like to download it, please contribute. Thank you very much.
Thank you for the presentation. Do you have any questions?
Did you try in your work to work on malicious applets?
Okay.
That you can install them on card and not on.
So the question is about malicious applets. So in this particular paper, we are not doing that. We are just working with the ordinary applets. But there is a body of work trying to usually evade JavaCard virtual machine restrictions. We did it as well. Nijmegen, Eric Paul, and his group was working on that as well. I think this is still the domain which is underdeveloped also in academia, because if you will look at all the papers that are presented here, that are really nice, but the academic researchers tend to work with something they control, right? Whereas the smart cards, it's one big black box, and just to start to do something, you need to really do a lot of analysis, a lot of guesses, and then maybe you understand how roughly they implement something, and then maybe you will find bugs there. But it's like a lot of steps, and you don't control. So I think we saw that or hear that people will do open implementations of the hardware, like simple crypto and stuff like that. That's great. I think we shall get something like that also with the smart cards, because otherwise this domain is like blind. Good.
You consider, because you only take the common criteria portal as an input, but several state agencies are very late to publish a common criteria portal, and you have public information at BSI and SSI available, correlated information. You might also have access to private scheme certificates, detailed information. But for your question about the commercial product, you might have public data sheet where you will have the list of algorithms. You focused on the sex inputs, but did you plan to investigate other sources, because it's quite difficult?
Okay, so basically the question is if we are planning or investigating the documents produced or provided by the vendors itself, right?
For free.
Yeah, for free. So our experience is we are seeing more concrete data in common criteria FIPS certificates than what the vendor is providing. Like, it's not always true, but most of the time it is. So like we were looking at what it's in the data sheets, but first of all, it's frequently not in some standardized form. You need to like manually go and check. And the second thing is usually it's we're more vague, because for example, for JavaCard, we can get the specific name of the constant, right? And we know exactly what's that. Whereas the vendor will say, okay, we support EC, Diffie-Hellman with this key length, but they will not tell us like how exactly they are preserving both coordinates.
Yes, it's indirect, but as long as we support a global platform version XXX, it's indirect information. It's mandatory. We have compliance tests to comply with. So you know implicitly that we will have all the constants to expect.
But with the global platform, you will get only some algorithms, like the algorithm necessary to.
An example, but
oh, okay, yeah.
Yeah. Yes, that's true in the datasheet. You will not find all the constants, but you will find the standard to comply with.
Okay, thank you very much. I will catch you, and I will try to discuss with you more.
I have a question again. Can you elaborate a little bit more on the motivation for the work? Because JavaCard is not the one, JavaCard forum is not specifying cryptography. They represent the constants that comes from other consortium, stakeholders, like you say, telco, banking, etc. And it's just the final representation, but Oracle what they pushed was different because they pushed a virtual machine, and why JavaCard survives so many years is the isolation of happens, and not really the cryptography. As you said, it's an hardware feature, it's not a JavaCard feature. And maybe to compare other ideas for studies would have been IDs pushed by Oracle, like RMI, remote method invocation, JavaCard web servers that was pushed just for open source community and never used because not come from stakeholders. So why, for your motivation, why you focus on JavaCard and crypto while JavaCard is not only crypto?
Okay, I think the short answer might be because for details about the crypto itself, we don't have the data. Like even in a, like you can see that in the certificates from common criteria that the details are omitted from the public information, right? Even like the vendors are getting additional points if the samples are not available and the details about the implementations are not available. So I think if that would be available, then great. But I think like we're not seeing these types of documents we can base the analysis on. But if you have them, no, okay, no, not like privately have them, but if you know where we can get them, then thank you.
Okay, so let's thank the speaker again. And now the second presentation of the session. PQ.V.ALU.E, PostQuantum RISC-V custom PQ.V.ALU.E extension on Dilithium and Kyber. And the work, this paper will be was written by Constantina Miteleludi, Jope Boss, Olivier Bronchin, Björk Fay, and Jost Drain, and Constantina will present the work.
Thank you very much for the introduction. Come from here. Okay, I know that I'm the last speaker before lunch. I will try to be fast. I'm Constantina, I'm a PhD student at PQ.V.ALU.E University. I'm very happy that I'm here today to present you this work. I did it during my internship at NXP. And I'm very happy that today all the speakers before me analyzed post-quantum schemes, so I don't have to go into details about how they work and what both schemes do. I will just speak about hardware design and hardware design choices. So that one. Okay, good. Okay, so we have heard already many times that quantum computing will threaten traditional public key cryptography because the mathematical problems that are based on the security, their security is based on, will be solved in polynomial time on a quantum computer using source algorithms. So the shift now, the research says that we need to shift to post-quantum cryptography. NIST is in the standardization process, and last summer it announces, among others, 2 algorithms for standardization: Crystal's Kyber and encapsulation mechanism, and Crystal's Dilithium digital signature scheme. So we need now, since we have these algorithms, we need to start implementing them. And we have many challenges to implement them, especially when we target constrained devices. And why we should target constrained devices? Because constrained devices nowadays are everywhere. They are in Internet of Things, they are in sensors, they are in healthcare, they are part of automotive processors. And of course, the basic characteristics that they have is the limited computational capabilities, limited memory, and also limited energy resources. So these are many challenges for someone that tries to implement these algorithms in these types of devices. Having this in mind, to target implementation of these schemes into small devices, we created a custom ALU that does the entity computation, that speed up the entity computations in both Dilithium and Kyber, and we integrated it in a 4-stage RISC-V pipeline processor. We extended the instruction set of this process of RISC-V with 10 new instructions that do modular arithmetic and the entity butterfly operations. And we managed to have an efficiency, we managed to reduce over 80% the cycle count compared to an optimized assembly that we have. And we also managed to not have a decrease on the operating frequency of the processor that we tested, but we tested its specific frequencies. I will go into details in the next slides. What do we mean by hardware accelerators? We have 2 choices. When we want to accelerate something, want to build a hardware accelerator, we can have 2 choices. The choice on the left it's what we call title coupled accelerator. It's integrated directly into the processor. It's part of the data path. Okay, it may take time and resources from the whole data path. And on the right, we have what we call loosely coupled accelerator, where that is goes as a peripheral. It is connected with the on-chip. It is connected with on the on-chip interconnect like any other peripherals and lives in parallel with the CPU. So basically, this can be part of the data path of the processor, and this we unload what operations we want to do from the processor to the accelerator, and then we send back the results back to the CPU. So for efficiency, we said that we have decided that we need to have hardware-software co-design in these schemes. We chose also to go to a title-coupled accelerator. So what are we going to accelerate from the whole scheme? We don't want to have the full scheme. We wanted to see specifically to do specific operations. So we started with a profiling. On the left, you see the cycle count of dilithium. On orange color is Keccak, which is the most dominant factor in the scheme. On green is the polynomial operations. Every column is the three functions of dilithium: the key generation, the sign generation, and the verification phase. Okay, and after the Keccak, we see that the next dominant factor is polynomial operations. But Keccak coprocessors, and there have been many in the literature. It's something that has been covered. So if we also measured, we use the Keccak coprocessor to also measure again the same numbers, and we verify that, yes, the dominant factor, the next dominant factor are the polynomial operations. So we want to accelerate this. We decided to accelerate this. This is a scheme of the number theoretic transform if we assume that we have 16 coefficients. For dilithium specifically, this is 256. I chose to show something simple here. So you see that we have a lot of operations. You see that we have a lot of overhead from the memory to go back and forth, load coefficients, store coefficients when we have results. So from where do we start? Let's see from where do we start. We start by the basic operation from going from layer one to layer 2. This is what we call a butterfly operation. This is a modular multiplication followed by modular addition and a modular subtraction. And for the backward entity that has a similar form, we have the gentleman's son, the butterfly, which is first the modular addition and subtraction, followed by the modular multiplication. We started designing the modular addition and the modular subtraction for these operations. So modular addition on the left, first we do, then our numbers, our inputs are assigned normalized to the range 0, Q-1 closed range. So we will do an unsigned addition first, and then we do an unsigned subtraction where we subtract the sum we subtract the modulus from the sum, and we decide at the end if we are going to take the initial sum or the reduced sum based on the borrow bit. And similar in the modular subtraction, we do first an unsigned subtraction, followed by an unsigned addition, and then we choose the result based on the borrow bit of the subtraction. We build that for having dilithium on our mind. And then we noticed that, okay, what would change if we wanted to cover Kyber in all this? Basically nothing. The operation is the same. The only difference between the two schemes is the size of the signals. We have 23 bits for dilithium and we have 12 bits for Kyber. So the only thing that changes is that here, when we use Kyber, from the 23 bits, only the 12 are useful. The rest, we don't use them. We can just safely ignore them. And another thing, the position of the borrow bit. It's the 24th position for the dilithium and 12th position for Kyber, which is, we will see later how this is being chosen. So with this design, we can cover basic operations for both schemes. Modular multiplication, then the third operation from the butterflies that we wanted to implement. First, we need an integer multiplication, and then we need the reduction. The reduction, in order to cover both schemes, we have dilithium's reduction and Kyber's reduction in parallel. Based on the scheme that we operate on our processor, on our ALU, we choose the correct result. For the reduction, we went for the Barrett reduction. to choose. Usually the original, the official implementation has Montgomery reduction. But when we noticed, we wanted to do it in hardware. And in hardware, but Barrett reduction is more efficient because it transforms the whole multiplication, division, all the operations that reduction must be done into addition, subtractions, and shifts. We know that in hardware shifts cost nothing. So basically our cost in Barrett reduction comes from the chain of adders and subtractors here, which is way less compared to a multiplier or a divider. And similar for the Barrett reduction for Kyber. Again, here we have shifts, additions, and subtractions. At this point, we say, okay, we have three modular operations. We have three circuits with three modular operations. We need to integrate them inside the RISC-V core. For our RISC-V core, we chose Pulpino. Pulpino is a four-stage, if it's a four-stage inline, it's a four-stage pipeline processor. This is a very simplified form that you see. You see basically the pipeline registers, three pipeline registers, and two stages, the decode stage and the execution stage. We modified, of course, the decoder because we wanted to support our new instructions. We modified the decode stage, and we added our custom operations here in parallel with a classic ALU. In our mind, because we target constrained resources devices, is to not increase the resources in the processor as it was. So basically, we took the outputs of the registers that go to ALU, we send them directly to our modular operations without increasing the pipeline registers. And basically, we managed to send maybe one or two control signals here in order to choose between the two schemes. So all the overhead in resources come from what we built here, and maybe one extra multiplexer, two extra registers, and that's it. Okay, we built that. Let me go one back. At this point, we say, okay, we can stay here. We have operations that last one clock cycle. They do the modular operations that we want. We can replace this inside the code of Dilithium, and we can be just fine. But Pulpino has a feature that don't all processors have. It has a register file that can give us three outputs. It has three read ports and two write ports. So if we go back and see again our butterflies, for our butterflies, our inputs are three. It's the coefficients and the twiddle factor, and our outputs are two. And again, for the Gentleman-Sandler butterfly, two coefficients, one twiddle factor, and two results to write back. With the feature that Pulpino has, this allows us to make these operations in one cycle. And this is what we did. We combined the modular adder, the modular multiplier, and the modular subtractor with some extra multiplexers in order to give the form of the two butterflies. And we also kept the initial operations, the modular addition, subtraction, and multiplication, as it was. So the data path now is like this. So the three, in one cycle, we can do the butterflies. In one cycle, we can do the modular operations. And we can have the overhead that we said. And these are custom instructions. We tried to keep them in the R format that RISC-V has. So basically, we have, this is our two source registers and one destination register. So the modular addition, subtraction, and multiplication basically follow the regular addition, subtraction, and multiplication, the same format, the same flow inside the data path. Okay, and for the butterflies, all three sections of registers become source registers, and the two source registers now become two destination registers. The instructions are divided, are only distinguished. They have the same opcode. They are distinguished by this funct, by this bit in the funct 7, which is also works as control bit in order to choose which reduction module, which modulus, and which scheme we are going to use. We built it, and now it's time to measure it. It's time to compare how fast we went with what we built. So this is the butterfly with custom assembly, Kulitaki and Gentleman-Sandler, Kulitaki on the left, Gentleman-Sandler on the right. So if we use Montgomery multiplication and CD butterfly, this mul age takes 5 cycles. So the Montgomery totally takes 8 cycles, and this here takes totally, I think, 15 cycles. But we managed to make it 1. In order to be fair, our comparison to be fair, we make two different comparisons. We assume that we don't have the special register file that Pulpino has, so we measure with the simple modular operations, like we do modular multiplication, then subtraction and addition, and similar for the GS butterfly. And we also measure with a special feature that Pulpino has. And these are the results for the polynomial entity. With blue, you see the initial number that we had with this code. And on the right, with orange, you see the PQ value, the version 1, 2. So basically this, and this is the orange, and then this and this is the green. So we managed to have more than 80% reduced in the clock cycle of dilithium. So let's see what we have for per phase. Per phase, we were here, and we went here. And again, if we remove again the ketchup coprocessor, it's more obvious how much was the speed up that we managed to gain. Okay, we have speed up. What was the resources? We have two goals. One goal was to speed up. The other goal was to not overhead a lot the resources of the processor. So we measured in FPGA. We have a 5.3 increase in LUTs, 0.7 increase in registers, and we have only 2 DSPs extra, and the 33.3, it's a little misleading. It's just 2 DSPs that we have, and these come from the integer multiplication. We also measured for ASICs. We used the 65 nanometers standard cell library, and we managed to have, we measured for various frequencies. For all these frequencies, we managed to, our modified Pulpino did not pass these frequencies successfully. So when we made as a timing constraint these 4 frequencies here, our design is inside these numbers. We did not exceed the cycle, the clock of the processor. So basically, we have around 15 to 16% increase in the resources of an ASIC, and we don't have increase in the clock. Okay, let's compare also. We measured, we analyzed, well, let's compare. What we compare, basically, we can compare with 2 other works. One already was mentioned during the PhD talk. It was Frintzman and Toll, the PQ.V.ALU.E. They also used Pulpino. Their difference is that they put it at the decode stage, and they managed to have increase in the total frequency of the clock, but they don't support dilithium, they support Kyber. And this work by Nanipieri et al., that they support both schemes, both dilithium and Kyber, in 2 different ALUs, but they target a different core. They target the CVA6, a 6-stage pipeline RISC-V core. So we can see that in the resources, we are lower than all, okay? But we can also see, we also wanted to compare Kyber. They implemented Kyber both works. So we wanted to compare. We are not faster than the PQ.V.ALU.E, even though we are lower in resources. So we wanted to show that, yes, okay, we can have a different overhead here. Yes, but you can have a different trade-off depending on what you want to do. You decide what you want to choose. So, to sum it up, we managed to build a custom ALU that is really lightweight, that supports entity computations for dilithium and Kyber, and we integrated it in a 4-stage pipeline RISC-V processor. We created 10 new instructions for modular arithmetic and entity butterfly operations, and we managed to have over 80% reduction in cycle without altering the clock of the processor for specific frequencies. And that's it. Thank you.
Thank you. So yeah, one question.
Yes.
Thank you for the talk. Can you tell us about the security of having the custom is there an impact of security?
We didn't measure any security. The devices that we target, we don't. It wasn't something in our goal. It wasn't in our goal to measure the security of that. To do in the future work, yeah, why not? I believe everybody's hungry. Sorry? I believe everybody's hungry.
Is there some question, another question? It's okay, there's also a question, so fine. And yeah, for the security, you talk about the security of the ALU, but do you plan to look after masked version of
Yes.
Kyber or
Yes.
Dilithium?
Yeah. If you mean if ALU can support this, if a custom ALU can support this, or
do you plan to
measure to see
and see
Yeah,
the
yeah,
impact
yeah.
on masked version?
I mean, yeah, it can be used for anything to measure anything, I assume.
Okay,
Thank you.
There is another question.
Yes.
So, do you use the Pulpino toolchain or
The Pulpino toolchain.
you did use that? The Pulpino toolchain.
You mean the library? The library? No, the original RISC-V. What RISC-V had?
It's for compiling when you add in new instructions, right? How do you have to modify the toolchain in order
I modified the toolchain, yes, and I rebuilt it.
to review it?
Yes. Yeah.
It's the newest GCC version. You didn't.
You mean if I upload it somewhere, if it's somewhere online?
Because I know that the Pulpino is GCC version 7.1.1, and so I don't know if you added new instructions. How do you, for your product, for example, how do you keep up with like updating the toolchain or the compiler?
Basically, you update two files where you put inside the description of your instructions. That's it. That's what we do. And then when we compile, we build again the library, and when we compile, the instructions are there. The compiler recognizes them, I mean.
Yes, and so it goes with your product, and the compiler goes with your product. So let's take a compiler now.
Yeah.
So let's send the speaker again.
So good afternoon, everyone, and thank you for the introduction. So I represent a PhD student at Sierra Research Institute in France, and I present joint work with Sana Boussam, a PhD student from Thales company France. So when Sana and I first got in touch, we discussed about a paper entitled "Keep It Unsupervised: Horizontal Attacks Mid Deep Learning" that was published at CHES in 2021. And this paper claimed extraordinary results in unsupervised horizontal side channel attacks using a deep learning-based iterative framework. From a glance to the abstract, we can right away be impressed by the quantitative claim of this paper. So the proposed iterative framework is initialized with a 52% accuracy from a bit-per-bit key recovery attack against a protected elliptic curve cryptography implementation, and improves such an accuracy up to 100%. So these promising experimental results lead us to take such a contribution as a starting point of our work. So we strive to reproduce results, understand the properties, benefits, and limitations of such a framework. Quite soon, we realized the black box flavor of the tool as proposed in the 2021 paper. Actually, it makes it very hard to understand its properties, to reproduce the results, and to assess benefits and limitations of the proposed technique. And this is what motivates the work I present today. So let me anticipate our contributions in a few words before going into details. So first, we highlight from the 2021 paper some properties of the used dataset and methodology. So namely the linear separability of the datasets and the overfitting of the framework. Once observed these properties, we realized that a very simpler and more efficient neural network would have been sufficient to obtain very good results, and so in a totally interpretable way. So broadly speaking, the used datasets were too easy to highlight any benefits provided by the complex approach proposed in 2021. And thus we confirm that fact by proposing a deep learning free alternative approach. Finally, as it is believed that deep learning deals well in noisy scenarios, we challenge the proposed iterative framework in a simulated noisy scenario to assess its robustness. But on the contrary, it allowed us to demystify the approach and observed the expected impacts of noise on its performances. At the end, a very high-level introduction about side channel attacks and some conclusions complete the agenda. So side channel attacks target cryptographic primitives when they are implemented on electronic devices by gaining information about sensitive variables from physical properties. So indeed, it is known that channels like power consumption, running time, or electromagnetic irradiation leak information about the executed operations and as well as the handled variables from a cryptographic implementation. So in some cases, in order to complete a key recovery attack, the attacker must gain information from a single acquisition trace, which leads us to talk about horizontal attack. It is the case when attacking some asymmetric cryptographic primitives, such as the scalar multiplication in an elliptic curve-based cryptosystem, that can be protected by several countermeasures, such as projective coordinates blinding or masking. An attack in that case is very analogous to a one-shot classification task. So the attacker must observe several parts of the acquired trace and assign to each the value of the handled qubit. In that case, supervised machine learning, which allows the attacker to train on a training dataset where trace parts are correctly labeled, may provide an efficient way to obtain optimal classification results. However, if a training dataset is not available, the attacker has to settle with unsupervised approaches, such as clustering algorithms. Unsupervised attack against protected elliptic curve cryptographic implementation was exactly the scenario tackled by Perrin et al. In 2021. Datasets used to perform experiments in the 2021 paper contain traces from two software implementations of an elliptic curve scalar multiplication provided by the Microsoft cryptographic library for ARM Cortex-M. Here, the scenario, the horizontal scenario, is forced by the presence of a projective coordinate re-randomization countermeasure, and most importantly, the fact that the used key is randomized so that no couple of traces processing the same key scalar is observable. The attacked implementations are in number of two, and the difference between them lie in the implementation of the conditional C-swap operation. So it's highlighted in the pseudocode visible here. The C-swap operation depends directly on the value of the key processed bits and is implemented by arithmetic means or by pointer swapping. So once traces are acquired, the proposed horizontal attack starts by splitting each single trace in subtraces, each corresponding to C-swap to a C-swap execution during the scalar multiplication. So at the end of the splitting phase, a trace corresponds to the 2055 C-swaps concatenation. And here, each subtrace Ti corresponds to the processing of the ith bits of the secret scalar. And at the end, the proposed attack consists in recovering such a 2055 bits. Since the attack is meant to be available in case of key randomization, the attacker is not provided with the knowledge of the key scalar S, and not even in a profiling stage. So at the end, the attack is performed in an unsupervised way.
Apologies.
Thank you. Okay. So here, two steps are proposed. First, applying a classical clustering technique. For example, here it's the K-means algorithm to pre-label the dataset, and then performing a corrective phase to enhance the accuracy of the previous cluster. So let us go into the details of the proposed corrective phase, which contains multiple steps.
Click in this again. Oh, I can't again. Can you try again? Click. Yeah.
Thank you very much. So we first consider the dataset, which contains traces pre-labeled as processing bit 0 and bit 1. And then we split the datasets at random into two datasets, the blue one and the yellow one. We train a neural network on the blue dataset in a supervised manner in order to let it classify the traces consistently with the pre-labels. And then we use the just trained neural network to predict labels on the yellow dataset. In the same way, we now train again the neural network using this time the yellow dataset, and then we use it to predict new labels for the blue dataset. So now that both blue and yellow datasets have new labels, we merge these datasets and shuffle traces to split them again into two new blue and yellow datasets, going back to step 1 and so on. So the claim is that after a certain number of iterations, labels become stable and the clustering errors have been corrected. So results obtained in the 2021 paper are summarized here on both datasets. They are obtained on 50 independent experiments, and both the average and maximum accuracy are observed. First, we can notice that the pre-labeling phase is somehow very unsatisfactory. Indeed, on average, the accuracy is around 52%, so it's just a little bit higher than the random guess. Then, by applying the iterative framework with a convolutional neural network that we'll be discussing later, the average accuracy raises up to 85% for the pointer dataset, and the maximal accuracy raises up to 76% for the arithmetic dataset. So the outstanding claimed results are reached by applying some regularization technique, namely the dropout and data augmentation. And this led the maximal accuracy reach 100% for the both datasets. So now we wonder why results raised that much by applying regularization techniques. So to us, this question was the first clue of a problem in the proposed strategy. So probably the proposed model was too complex, leading to overfitting. Let's try to enter to this question by opening the black box dimension of the iterative framework and trying to understand its working principles, its properties and limitations. So we started our analysis trying to interpret the results obtained in the 2021 paper. To do so, we authorized ourselves to assume the knowledge of the two labels in order to perform a Welsh t-test and characterize the two datasets. As we can see, both of them have significant side channel leakages. Indeed, for the pointer dataset, sample maximizing the t-value seems to be around 600 to 650 samples and around 3,300 to 3,350 for the arithmetic dataset. So we use this knowledge to perform a point of interest selection and to apply the K-means algorithm on narrow interesting regions. In this way, we obtain very high clustering performances. So this highlights the fact that the K-means algorithm is sufficient to discriminate subtraces processing bit 0 and bit 1. So therefore, we deduce that the classification problem is not so complex to solve, as both classes can be separated by a K-means decision boundary. And as we know that the K-means decision boundaries are hyperplanes, we conclude that a linear classifier would be more suitable for the underlying classification problem on both datasets. So if a linear classifier should be sufficient for the underlying classification problem, the proposed convolutional neural network, which includes hundreds of neurons and several nonlinear activation functions, is maybe too complex. So let's try to simplify this neural network model. Our proposal is to settle with one neuron so that we actually use a linear classifier. And we remark that if we obtain good results, it would confirm that the iterative framework allowed an hyperplane to place in space in such a way to separate the two classes. And of course, the advantage of such a light architecture is huge in terms of time and memory complexity. So let's get to the results. For both datasets, we use the same initial labelization obtained in the original paper. So the accuracy at the beginning is about 52%. And we can see that the iterative framework with the simple perceptron allows the average accuracy to raise up to almost 99% in about 20 iterations, and this without applying any regularization. So this is for the pointer datasets. Concerning the arithmetic datasets, results are less impressive. The achieved accuracy is about 70%. But we note that these results are still better than those obtained in the original paper without regularization. However, this is still not sufficient to consider the attack as successful. So in this case, we decided to reduce the size of the subtraces. So we considered a smaller number of time samples in order to observe if this way the framework manages to correct mislabeled subtraces. Thus, we narrowed down the subtraces from 8,000 samples to 2,000 samples. And this simple region selection allows us to obtain again an average accuracy of 98%. So these results are obtained without regularization technique and with a very simple neural network. So it highlights the fact that even in a non-profiled context, a linear classifier is sufficient to correct mislabeled subtraces. So this means that the proposed deep neural network was definitely oversized. As a general fact, deep learning architectures provide advantages with respect to conventional techniques when dealing with noisy data or complex problems such as nonlinear decision boundaries. But datasets used in the original paper do not have such characteristic. Thus, it does not allow to assess the suitability of the iterative corrective framework in interesting cases. For this reason, we tried to identify the benefits and limitations of the proposed strategy in a simulated noisy environment. To do so, we started from traces from the pointer datasets that we visualized here in a plane using the TSNE technique. And then we added Gaussian noise with several levels of standard deviation. So here we use two different levels, and we remarked that doing so, the famous linear separability properties is lost and that clusters become untangled. In this context, we consider our two architectures, namely the single perceptron and the CNN model proposed in 2021. And we use them in two different ways. So first, we use them in a supervised way to perform classification and estimate a correct upper bound. And then we use them in the unsupervised corrective framework in order to observe the capability of this iterative framework to reach the upper bound. So here we observe the following results. With a small level of noise, we obtain a very high accuracy in the supervised manner using the CNN architecture. And the iterative framework also succeed in almost reaching the same level. Nonetheless, by raising this noise level, the problem becomes hard to solve, and so even in the supervised fashion. So the upper bound accuracy with the considered CNN architecture is around 79%. And in addition, the ability of the iterative framework to correct mislabeled data drops dramatically. And now if we look at the simple perceptron model, we observe that results are very similar. So in conclusion, the higher the noise level, the harder it becomes for the framework to correct wrong bits. And so regardless of the neural network model considered. So this is a limitation of the iterative approach that does not correctly deal with entangled clusters. So we finally wondered if it's really necessary to pass through this advanced tool instead of applying classical statistical tools. And this is what we do in the last part of the paper. So we show that the use of the iterative framework was finally not mandatory in the context it was proposed. To perform this alternative unsupervised attack, we applied a very well-known feature extraction technique, namely the principal component analysis. And then we use the k-means algorithm over a single principal component. So of course, those of you who already used this technique before are wondering how we dealt with the component selection issue. Indeed, PCA provides as many projecting components as the number of time samples. And it has been observed that the first components that are the one that maximizes the variance of the projected traces does not always contain the most useful information. So to choose the components, we tried 3 strategies. We used the natural order, visual selection, and a third methodology called explain local variance that was proposed at CARDIS in 2015. And in addition, we also observed that this ELV technique came with a useful denoising strategy. So here we observe the graphic of the cumulative ELV for the first components on the pointer dataset. So the components that would be primarily selected by the ELV strategy is the one highlighted in red. So it's the 8th component, and it's actually turned out to be the one that leads to the best attack results. On the contrary, the situation is a little bit harder for the arithmetic dataset. So here we have in green the component that would be first selected by the ELV technique, but actually the best results are obtained with the component depicted in magenta. So if we look at the results and compare them with those obtained in the 2021 paper, we first observed that the average attack on the pointer dataset was not successful with the CNN-based iterative framework. Indeed, 91% of accuracy corresponds to 23 wrong bits on 2056 on average, which requires 2 to the power of 109 operation to brute force and complete the attack. So such a remaining effort is considered unaffordable. On the contrary, our best results allow us to conduct a successful attack as we achieve 98% of accuracy, which corresponds to 2 to the power of 33 operations to complete the attack. Concerning the arithmetic dataset, both the iterative framework and the classical strategy fail in obtaining a successful attack on average. However, if we look at the maximal accuracy, we observe that even if our classical approach do not achieve the 100% accuracy that we obtain in the using the iterative framework, it still allows to conclude a successful attack by means of 2 to the power of 58 complementary operations. So in conclusion, the iterative framework free approach leads to at least the same successful attack as the approach proposed in 2021 for the studied case. So at the end, our work showed that the attack proposed in 2021 was biased by the simplicity of the used datasets, and such a simplicity was hidden by the huge complexity of the proposed deep learning-based solution. We also show that moving to a more complex scenario, the iterative framework is strongly impacted. So this led us to question the use of very complex machine learning solutions for general problems. Indeed, we show that focusing on the simplest possible attacks gives better insight on the actual threat. So at the end, in cases where machine learning techniques are required, we recommend to conduct an in-depth analysis to size it carefully. Thank you for your attention, and I'll answer your question.
Thanks a lot for the presentation. Any questions? One?
Thank you for the presentation. My question is why they missed the fact that it can be done way easily and in a simpler way. What do you think?
I don't really know, but I think maybe they just find the corrective approach interesting, and they wanted just to assess its success rate in the simple cases, but I think maybe they should have mentioned it, that maybe there were a simpler approach. I don't know.
Did you try multivariate classifier?
No, we only tried the approach using PCA and Canines, because we wanted to just replace the point of interest selection that they used in the paper and show that there were more common way to proceed. Because the point of interest selection method that they used have been proposed by one of the authors also.
Other questions? But one very philosophical one. Can you go back to one slide?
Which slide?
The previous one.
Oh, okay.
Was captured by in case machine learning is needed, which I really appreciate it. Are we abusing machine learning beyond what you have already saying? What's your feeling?
I think yes, because I've studied other horizontal and unsupervised attacks where some authors used machine learning models, and I was able to achieve the same results with very simple models like linear discriminant analysis or things like that.
Thanks. There are no other questions. Thanks. Check the slides.
So thank you for the introduction. And I'm Dorian Yamata, a PhD student from the CEA and the Uber laboratory. And today I will propose you a new study of deep ensemble learning applied to profiling side channel attack context, with an experimental exploration of the stacking allegation, in which a meta model is trained to learn how to combine the ensemble prediction. This work is a joint work with Eleonora Cagli from the CEA and Rémi Hérault, Vincent Glosso, and Lilian Bossuet from the Uber laboratory. So first of all, let's start with a bit of background on side channel attacks and ensemble learning. Side channel attacks are physical attacks based on observation. The aim of this attack is to exploit physical leakage unintentionally emitted by a device when it performs cryptographic operation, such as power consumption or electromagnetic traces, which can be collected as depicted on the slide with an oscilloscope connected to a probe placed on the top of the device. An attacker or a security evaluator will be able to, by the exploitation of these physical leaks, to retrieve some sensitive data and finally break the device security by recovering the secret, which is typically a secret key. In this work, we consider profiling attacks. So in the profiling scenario, we assume that the security evaluator has at his disposal another device called the clone device, identical to the target one, but in which he has full control. So he can first characterize the leakage on the clone device in supervised manner, and then use the characterized leakage to attack the real target device. Profiling side channel attacks can be performed with machine learning techniques, and nowadays deep learning is widely used. To perform profiling SCA with deep learning, a neural network model is trained on the profiling data to assign for each profiling traces a corresponding sensible value. And once the model is trained, it could be applied on the target traces. If the model has a good enough generalization, this means that the model is able to properly work on new data not seen during its training. So in this context, that the model is able to properly work on the target traces. Therefore, the security evaluator will be able to retrieve the secret key. Deep learning is a powerful method to perform profiling SCA. However, designing an efficient neural network model in SCA context can be a difficult task that may require laborious hyperparameterization efforts. Designing an efficient neural network model is complex in deep learning in a SCA context. Neural networks may have much more tunable hyperparameters than other techniques. For some, I relate to the architecture design, like by example, the number of layers or the type of layer, or the number of neurons per layer. And others are related to the tuning process, by example, the set of the batch size, the loss function, the optimizer, the number of learning epoch, or the set of the learning rate. And efficient automated hyperparameters tuning is not solved yet, so hyperparameters are generally researched by experimental analysis. And their correct configuration is essential to obtain a good generalization, and in our case, a good attack performance on the target device. And the more complex the architecture, the greater the hyperparameterization effort is necessary. So, in machine learning community, in order to reduce this hyperparameterization effort and improve generalization, a common approach is to use ensemble learning. Ensemble learning consists in training different weak model and different model, which are generally weak, and aggregate them with an aggregation method to construct the final ensemble model. Combining complementary weak model prediction can thus improve generalization and in our case lead to better attack performance on the target device. Concerning how to aggregate the weak model prediction, in this work we use two meta algorithms. The first one, the bagging aggregation, perform an averaging or voting process to aggregate the weak model prediction. On the other hand, the stacking aggregation use the meta model training to learn how to aggregate the weak model prediction. Deep bagging ensemble has already been explored in SCA context. So in this work, we use it essentially as baseline to benchmark stacking aggregation. There are several differences in terms of implementation between the traditional machine learning bagging and the SCA variant bagging proposed in the previous work, notably the bagging process proposed in the seminal work of deep bagging ensemble learning applied to profiling side channel attacks, published in the CHESS conference in 2020 years. First, in the traditional machine learning bagging, the training set is very subsampled in order to train the weak model on different data and promote diversity between their errors. But in SCA, the profiling step requires a high number of traces. So like on the previous work, in this work, we did not subsample the training set. Another difference is that the aggregation is not directly performed on the weak model prediction, but during the computation of the summation of log probabilities for each key hypothesis, so during the attack step and the computation of the rank metric. Bagging aggregation has some no limitation. First, as each weak model contributes equally to the ensemble prediction and independently of the individual attack performance, there is a potential problem in presence of performance gap between the weak model. Another limitation is that the bagging process takes its force from the diversity between the weak model prediction and consequently between the complementarity between the weak model error. So an ensemble of a weak model with a lack of complementarity between their error can lead to an ineffective bagging ensemble. In stacking aggregation, an higher level model called meta model is trained on the weak model prediction to learn the best way to combine them and construct the final ensemble prediction. So in this context, the meta model can be seen as a leader which decides how to combine the weak model prediction. Therefore, this is a new constraint in our ensemble attack because the ensemble success depends on the ability of the meta model to properly learn how to combine the weak model prediction. So a poorly meta model can lead to an ineffective ensemble attack. When we consider stacking aggregation, a good practice is to train the meta model on different data used to train the weak model. Because if we use the same data, this carries a high risk of overfitting. So if possible, and we have enough data, a good practice is to train the weak model on the training dataset, and then use the weak model prediction on other data, like by example, the validation dataset to train the meta model. And finally, get the ensemble prediction with the meta model inference on the weak model test prediction. But in our case, due to the lack of validation data, we made the choice to use the weak model prediction on the training dataset to train the meta model. And therefore, we consider the risk of overfitting during our experiments. So now that the background and context has been given, let's move on some experimental results. We experiment on several publicly available AES datasets, which include different kinds of countermeasures. The first one, the AES-AG dataset, does not contain countermeasure, but has the particularity to be very noisy and also to be an hardware implementation of the AES. We also experiment on the different version of ASCAD dataset with fixed and variable key for training traces. ASCAD dataset contains a first-order masking countermeasure and has the ability to add a parameterizable desynchronization effect on the traces. Concerning the metric used in this work to evaluate our weak model and ensemble model, we essentially use the number of attack traces required to get a constant guessing entropy to 1 that will denote NA during our experiments. So to describe our experiment settings, in order to evaluate bagging and stacking ensemble, we first train for each dataset 10 neural networks, including MLP and CNN with random architectures.
We always target one SBox output as sensitive value. It may assume 256 possible places. And note that we rank our 10-week model by the attack performance in order to increase the ensemble size by decreasing weak model performance. We made this choice in order to take the point of view of a security evaluator who knows his weak model performance and wish to use a posteriori ensemble learning to improve his attack. Next, our experiment consists in training for each ensemble size 40 random meta model. We try to use as meta model different MLP with some random hyperparameters, and we set an only stopping criterion to control the learning process and avoid overfitting. Note that our 40 random meta model are the same for all dataset and all ensemble size in order to properly check the meta model behavior across different configurations. And finally, we can check the robustness of stacking ensemble and compare it with the performance of the bagging ensemble baseline and the best single weak model baseline. Intuitively, an excellent ensemble is one in which the models are both accurate and complementary between their error. But in our case, after the training of our 10-week model for each dataset, we found 3 different kinds of problems. First, on the ASCAD fixed key version without desynchronization, we have an ensemble of weak model with a significant performance gap. On the other hand, on the ASCAD variable key version with desynchronization, we have an ensemble of weak model with similar attack performance, but with very close prediction. So we have an ensemble of weak model with a lack of diversity between their prediction, and consequently a lack of complementarity between their error. And finally, on the ISLG dataset, we don't observe particular performance gap or lack of diversity problem, but our weak model are all very poorly due to the high level of noise of the dataset. This configuration is very interesting because we have 3 different kinds of scenarios in which the bagging aggregation can be impacted. And concerning the latest dataset, so ASCAD variable key without desynchronization, we don't observe particular weak model problem. So the results of this dataset are out of the scope of this presentation in order to focus on the comparison between bagging and stacking ensemble for the other datasets. So let's start with ASCAD fixed key version without desynchronization, which contain a significant performance gap problem between the weak model. This table depicts the performance of our 40 random meta model across all ensemble size. The NBase success column refers to the number of meta models that improve the attack performance compared to the best single weak model baseline. Concerning the attack performance, the NI value are estimated considering only successful meta model, and the best result is highlighted by a green cell. We also report for each ensemble size the best improvement in number of traces, which correspond to the best meta model trained for each ensemble size. We observe that on this dataset, stacking ensemble can improve the overall attack performance by more than 59%. And the best stacking improvement was obtained on the ensemble of 4 weak model, with a meta model that improves the attack performance compared to the best single weak model baseline by more than 80%. However, we observe that by increasing the ensemble size, the number of successful meta model tends to decrease. We initially think that the weakest model impacts and penalizes the ensemble performance. But in fact, the addition of weak model and their knowledge in the ensemble, even less and less efficient, makes the meta model learning task easier. And on this dataset, stacking ensemble often become overly complex for the learning task, and therefore the meta model overfit quickly without learning relevant information. We can observe the average early stopping behavior and see that up to an ensemble of 5 weak model, the average learning epoch before overfitting is 40 learning epoch. But from an ensemble of 6 weak model, the meta model began to overfit in an average of just 2 learning epoch. So now let's compare bagging and stacking performance. The left plot represents the guessing entropy convergence for the best single weak model and the best bagging and stacking ensemble. We can observe that stacking ensemble, which is depicted on the graph with a green curve, allow better and faster guessing entropy convergence and therefore better attack performance compared to the best single weak model baseline and the best bagging ensemble baseline. But the most interesting comparison is the comparison between bagging and stacking ensemble across all ensemble size, which is depicted on the bar plot on the right, where the blue dot line represents the best single weak model baseline in terms of attack performance, and the orange and green bar represent the bagging attack performance and the best stacking attack performance for each ensemble size. We observe that on this dataset, the performance gap problem has strongly impacts the bagging aggregation. By adding less and less efficient weak model in the ensemble, bagging aggregation become less and less suitable and result in an ineffective bagging ensemble when we consider all 10 weak model in the ensemble. And on the other hand, stacking aggregation proved to be more robust and allows significant attack improvement across all ensemble size. This may be explained by the fact that a properly trained metamodel is able to learn the relevance of each weak model during its training. So now let's move on the result of the dataset ASCAD variable key version with desynchronization, which contain a lack of diversity problem between the weak model prediction. First, if we take a look at the best improvement in number of traces for each ensemble size, we observe that on this dataset, stacking ensemble can improve the overall attack performance by more than 76%. And the best stacking improvement was obtained on the ensemble of 7 weak model, with a meta model that improves attack performance compared to the best single weak model baseline by more than 80%. It is interesting to observe that on this dataset, stacking aggregation and meta model training proved to be more robust. Adding weak model did not decrease the number of successful meta model. This may be explained by 2 reasons. First, on this dataset, the prediction task is more complex due to the presence of high desynchronization effect on the traces. And secondly, because the weak model have very close prediction due to the lack of diversity problem. So the addition of weak model in the ensemble had very few knowledge, and therefore, stacking ensemble didn't become overly complex for the learning task, and the meta model did not immediately overfit like on the previous experiment. Now, if we compare bagging and stacking ensemble across all ensemble size, we observe that on this dataset, the lack of diversity has strongly impacted the bagging aggregation, leading to poorly or even ineffective bagging ensemble. And on the other hand, stacking aggregation allow better and significant attack improvement across all ensemble size. This may be explained by the fact that a properly trained meta model is able to learn even from small variation between the weak model prediction. Now let's take a look on the result of the dataset AES-HD with an ensemble of weak model with very poor performance. First, we can observe that on this dataset, stacking ensemble improves the overall attack performance by more than 93%. Stacking ensemble is particularly interesting for this dataset, allowing significant attack improvement and successful attack with less than 2,000 of traces for each ensemble size by using ensemble of weak model, which independently need more than 20,000 of traces for a successful attack. We also observed that stacking allegation and meta model training proved to be robust on this dataset. Adding weak model did not decrease the number of successful meta model. This is because on this dataset, the weak model are all valued poorly. So in a similar way to the previous experiment with the lack of diversity, the addition of weak model in the ensemble had very few knowledge, and therefore stacking ensemble didn't become overly complex for the learning task, and the meta model did not immediately overfit. Now, if we compare bagging and stacking ensemble for each ensemble size, it is interesting to observe that on this dataset, bagging aggregation work well because there is no performance gap or lack of diversity problem. However, we notice that the bagging improvement is limited by the poor performance of the weak model. And on the other hand, stacking aggregation result in work better and result in better weak model combination and much greater improvement in attack performance for all ensemble size. So to summarize, in our experiment, stacking ensemble has always outperformed bagging ensemble and the best single weak model baseline by providing significant attack improvements across all datasets and all ensemble size. In particular, we observed that stacking aggregation is less impacted by the individual performance of the weak model, since a properly trained meta model is able to learn the relevance of each weak model during its training. We also observed that stacking aggregation is less impacted by the lack of diversity between the weak model prediction, since a properly trained meta model is able to learn even from small variation between the weak model prediction. So when we consider stacking aggregation, the choice and the number of weak models to use in the ensemble are less decisive for the ensemble success, which makes stacking a more flexible aggregation method for security evaluator interested in using a posteriori ensemble learning to improve his attack. However, we noticed that stacking aggregation is prone to overfitting. In particular, we observe that stacking ensemble can become overly complex for the learning task, and therefore the meta model may be overfit quickly during the training process without learning relevant information. Overfitting has notably been observed when the ensemble of weak model had a good diversity between their prediction and a good complementarity between their error. But on the other hand, in an interesting way, we observed that our two-layer meta model as always properly generalize and improve attack performance across all datasets and all ensemble size. Therefore, our experiment suggests that there is no need for complex metamodel when we consider stacking ensemble in SCA context. So now for a quickly comparison with state-of-the-art architectures, during our experiment, we observed that stacking ensemble can provide with less effort similar attack performance to efficient architectures proposed in literature. Notably, we observed that stacking ensemble can provide similar attack performance to efficient architectures which have been hyperparameterized by extremely time-consuming process, such as reinforcement learning technique for an automated hyperparameter tuning, or a fine-tuning hyperparameterization performed with significant human effort. So our experiments suggest that stacking ensemble appeared to be a suitable approach to limit the need for the security evaluator to perform a fine hyperparameterization of its architecture. And as a takeaway messages, first, we would like to clarify that we don't claim that ensemble learning completely replaces hyperparameters tuning, but ensemble learning can relax the need for hyperparameterization. In our experiment, we extend the previous work which used deep bagging ensemble in SCA context. In particular, we highlight some of the limitations of the bagging aggregation and show how stacking aggregation results in better attack improvement while providing a flexible solution to address this limitation. Notably, stacking aggregation is less impacted by the weak model performance and also by the impact of the lack of diversity. We also found during our experiment that a limited ensemble size is enough to build a strong and deep stacking ensemble. So stacking ensemble appeared to be a suitable approach to limit the need for the security evaluator to perform a fine hyperparameterization of its architecture. As a counterpart, when we consider stacking allegation, we add a new constraint in our attack because the ensemble success depends on the ability of the metamodel to properly learn how to combine the model prediction. So a polymeta model can lead to an ineffective ensemble attack. And we also found that stacking ensemble is prone to overfitting, but during our experiment, overfitting is promoted by the fact that we use the weak model prediction on the training dataset to train the meta model. If possible, and we have enough data, it could be interesting to use other data like the validation dataset to limit this overfitting phenomenon. And we also found that there is no need to consider a complex meta model for stacking ensemble in SCA context. Using a simple meta model can even avoid overfitting. And during our experiment, our smaller meta model was 2-layer MLP. But with the feedback of our experiment, we think that it could be interesting to further simplify the meta model architecture. And finally, in future work, we think that it could be interesting to explore other deep ensemble learning in SCA context, like, by example, the boosting ensemble learning, which aggregates the weak model prediction in a sequential manner. So thank you for your attention. And if you have any questions, I'll be happy to answer them.
Questions? Yeah.
Together with the first stroke, it really looks like you've been pushing too much of deep learning over the last 2 years. So do you think like the data set so simple tools to just divide some points?
Can you repeat the question for the people online? Probably you did it. Yeah.
I thought
I can repeat.
Yeah.
It looks like we've been pushing deep learning a little bit too far, or I mean, yeah, some unformed claims maybe about deep learning. And do you think that, and with the also the previous one, this time you try to come back to something simple, more simple at least. And do you think that at some point we will use again the data factors that will rate the data factors we can do?
Yes, I work with deep learning model. Yes, I know template attack, but our work showed that there is no need to consider complex architectures, like it's a common way in a SCA context. But I don't think that I continue to try a template attack because we prefer explore automated approach with a deep learning model.
Other questions? I have one quick one. If you can go back some slides, there was a certain point, a graph in which you were showing the amount of trace improvement. This one?
Yeah,
the previous one. This is around 80, but this is almost 95%. Is there any specific feature?
Yes, this is the result of our best meta model trained for each ensemble size. So the best attack improvement that we get during all of our experiments. So the best meta model trained for the best ensemble size. And this is the same for the bagging improvements. It's the best ensemble size which improve the improvement, so which improve the attack performance. Sorry.
Okay, thanks. Any other question? Now let's take the speaker again.
So, hello everyone. Thanks for the introduction. So my name is Raphaël Joude. I'm a PhD student working in the joint lab between CARDIS again and Mines Saint-Etienne. And I'm here to talk about a work names like an open book written on network architecture with simple power analysis on 32-bit microcontrollers. This work is a collaboration with Pierre-Alain Moëlic, Simon Pontier, and Jean-Baptiste Origo. So after a brief introduction word, I'll describe the challenges and the scope we set in before talking about the proper experiments we've conducted. And then I'll briefly conclude and share the worries and perspectives arising from this work. So today, an important trend in machine learning is the deployment of those models on embedded systems. It involves a wide variety of application and hardware platforms such as FPGAs or microcontroller. However, this deployment raises many questions regarding machine learning security and the related attack surface. When targeting a machine learning model, we usually distinguish attacks targeting its integrity, its availability, or its confidentiality and privacy, which is the focus of this presentation. Targeting confidentiality is threatening everything that is related to intellectual property of a model, such as its finely tuned parameters or architecture. So, as you see in this presentation, machine learning isn't a tool we are going to use alongside side channel analysis, but is the target of those analyses. So I mentioned the attack surface related to the model deployment. So in the beginning, the majority of attacks were algorithmic one in a way that they were targeting the theoretical flows of machine learning models. However, now that model deployed on physically accessible devices, new attacks can leverage on implementation flows and use analysis such as fault injection or side channel ones, which are the focus of this presentation. So now let's discuss a bit more about the challenges and the stakes related to model architecture. So today, deployed models are either based on already existing architecture or handcrafted ones. And those architecture are often required in order to perform other kind of attacks that are targeting either model integrity, availability, and confidentiality we mentioned before. And as an example, on the right of the slide, you have a table gathering few attacks targeting the extraction of model parameters. And what they have in common is that they all require the knowledge of the targeted model architecture, even if they use different attack surface or different method. And here are the model, the paper, the studies related to proper architecture extraction. Such paper often use cache attacks or memory access pattern in order to recover architectures from complex systems such as FPGA or GPU. However, here are represented studies that are using power consumption or electromagnetic emanations in order to recover information from the architecture. And if we look at the works dedicated to microcontrollers, there's no work leveraging on the repetitiveness of deep neural network model computation, which could leak information regarding the architecture through the electromagnetic emanation, as an example. So to be clear that we are all talking the same languages, what is a simple power analysis? So it's simply the direct interpretation of power consumption or electromagnetic emanations collected during a sensitive operation. This can allow to identify secret information in some cases, as illustrated on the right of the slide, or to identify piece of code and area on which mount other attacks. So now let's discuss about the scope and the proper objectives we set. So our goal is to extract as precisely as possible architecture of deep neural network model that are embedded on an STM32H7 board. Those models are quantified, meaning that their parameters are stored on with 8-bit variables, and as well as their computation. They are functioning using 8-bit variable as well. And those models have been quantified and then implemented thanks to open source libraries, which are NNOM and CMCCNN by ARM. The fact that those libraries are open source is important because it allows us, as well as an attacker, to analyze the C code related to each layer and then anticipate the corresponding electromagnetic leakages related to them. Another point to be mentioned is that in our experiment context, we chose to disable the cache optimization available on the board. Regarding the attacker, we place him in a black box context in a way that he has no knowledge about the model architecture to extract no model parameters. However, he is aware of the usage of CMCCNN library. And the last point, but not the least, that implementation offered by CMCCNN library are inconstant regarding the execution time. So in order to avoid the synchronization problem, we chose to acquire few traces with a single input and then average them together. So here are the two kind of architecture we studied. So there's the multi-layer perceptron, where are simply dense layer stacked horizontally with neurons connected together, and convolutional neural network, which had some feature extraction layers such as convolution and pooling one. And here are the model we developed and we targeted for our experiments. So what is important to see here is that for every different color, each different color corresponds to a different kind of layers, and we'll go through the detail of each of them in the next slides. So we trained both MLP and CNN either using the Cypherton on the NIST datasets. And on the right of the slide, you have a table gathering all the hyperparameters that we targeted and we wanted to extract it. Those corresponds to the most common one for regular layers, such as convolution or dense one. Another point that we want to distinguish is the activation function that is used, if it's the rectified linear unit one or not. So now let's jump into the model analysis properly. So starting from the overall shape of an inference traces, there's 3 steps for an attacker to recover the architecture, the detailed architecture of the model. The first point is to identify the number of layers. This can be done pretty straightforwardly, simply with the naked eyes. And in some more complex cases, an attacker could rely on frequency spectrum analysis. Once this number of layers is identified, the point is to get their nature. So an attacker could use the layer execution time and the underlying complexity. So we're not going to discuss about this point in this presentation, but it is in the paper. And another way to identify the nature is to use a pattern that are specific to different kind of layer. And once all layers are pointed out with their nature, the remaining step is simply to perform the proper hyperparameters extraction technique for each layer one after the other. and recover the details about the architecture of the model that is targeted. So here are the three different models I introduced previously, and here are the electromagnetic traces that corresponds to them. And you can see that the identification of different kind of layer is pretty straightforward, especially for the convolutional layer, which are represented in blue or the dark in yellow. However, in some cases, like the sequences of dense layer, and especially when having a reduced number of neurons, the attack can be a bit harder. So an attacker could leverage on frequency analysis in order to properly point out the layer boundaries. But all those analyses can simply be done with the naked eyes, which is the important point here. So now let's discuss about the proper layer analysis one by one, starting with the convolutional layers. So on the top right, you have a glance at what is happening in a convolutional layer and the hyperparameters that we are targeting. So there is the output dimension of the output tensor, the dimension of the output tensor, sorry, as well as the number of convolutional kernel that are used and their size. So on the bottom of the slide, you have a glance at the general convolution implementation of the CMC-CNN libraries. And what is important to see here is that there are two for loops that are iterating directly over the H out value, which we are targeting. And if we look closely at the number of gem function call, it is called 1 out of 2 time because of the if statement at the line 4. This means that an attacker able to count the number of occurrence of the gem function from the electromagnetic traces can recover the value of H out. So here are the traces corresponding to 2 convolutional layers of the model we presented before. And there are some appearing patterns that can simply be counted out in order to recover the H out value. And such results have been also obtained for all the other convolutional layers of the model we targeted and we presented before. And for the remaining hyperparameters of the convolution function, what is interesting is that an attacker can leverage on the kind of Rochandol effect in a way that by zooming inside the patterns that we introduced before, we are able to discover other patterns that are related to the K hyperparameters we want to extract, which is the number of kernel of the layer. So if we go back to the algorithm of the gem function we mentioned before, as before, there's a for loops iterating directly over a variable based on the K hyperparameters value, meaning that by counting the number of patterns, an attacker is able to recover the link between this number of occurrence and the K hyperparameters value. And as before, by looking at the electromagnetic traces, we have been able to recover the number of kernel that were used in the convolutional layers of the models we targeted. And we continue to repeat the Rochandol effect by going one stage deeper in order to recover the Z value, which is the size of the kernel. So as before, there is a for loops iterating over a variable defined based on the Z value. So meaning that by counting the number of iteration of the pattern that you can see here, with the knowledge of the number of channel of the input tensor, an attacker is able to recover the Z value. So in order to remind what the Rochandol's effect, so it allows us to progressively recover different hyperparameters such as H out, K, and Z. And once those 3 hyperparameters are extracted, the attacker simply can deduce the stride and padding value that are used by the layer, because the padding value is necessarily smaller or equal than the size of the kernel that is used. So now let's jump to max pool layers. So as before, the 2 hyperparameters we want to recover is the dimension, of the output tensor, as well as the size of the pooling filter. And what is interesting here is that if we look at the algorithm, it's divided in two distinct parts. The first one is affecting the pooling operation along the x-axis through the usage of two different for loops, while the second one is performing the pooling operation along the y-axis through a single for loops iterating directly over the h-out value. And those two different parts can be found again in the electromagnetic traces that corresponds to the max pool layers, meaning that by targeting the second part of those traces, an attacker is simply able to count out the value of h-out because of the patterns that appear, which are pretty visible and distinguishable one from the other. Next is the dense layer. So here, as before, what is important to see here is that there is a for loops iterating over a value based over the number of neurons of the layer, which are managed by groups of 4, meaning that, as well as before, by counting the number of iterations, an attacker is able to recover the number of neurons of a dense layer. However, those cases correspond to the case where there's no remainders to be managed, as neurons are grouped by groups of 4. So what happens when there are remainders to be managed? So in the algorithm, there's another for loops that is iterating over a different variable. And what is important here is to see that the neurons are handled independently. This means that there would be another electromagnetic activity appearing afterwards, the one we already saw just before. And in order to verify that, we designed a new model with dense layer having a specific number of neurons, which would produce those remainders and induce those remainders to be handled. And for the first example here, we have a layer having 23 neurons. So we found back the 5 first groups, the 5 first pattern corresponding to neurons being handled by groups of 4, and then there are 3 remaining ones at the end as expected, corresponding effectively to the 23 neurons that we're supposed to found in the corresponding layer. However, for the next layer, such analysis is a bit more difficult and can hardly be done simply with the naked eyes, because the length of the patterns that are to be seen directly depends on the vector input shape. So when it's the smallest it is, the smallest the pattern to be seen will be, and will be harder to simply point it out simply with the eyes. However, in order to verify that neurons were treated as we expected, we add illustration triggers in order to verify the groups of neurons were handled the same way. So we can see here that neurons are handled as we expected. Even if this analysis is a bit more complicated simply with the eyes, we can leverage on pattern detection tools in order to simply recover those values. And finally, regarding the activation function, the point was to distinguish the usage of the rectified linear unit in comparison to 10H or sigmoid functions. And the main hints regarding that here is the duration of the activation function, because the rectified linear unit function is much simpler compared to the two other, as there's no dividing operation nor exponential computation to be performed. Another hint is the patterns appearing in the electromagnetic leakages that are slightly different from the ROLU compared to the other, especially when we are looking at the duration of those patterns, allowing to have additional hints regarding what activation function is used in the model that we are targeting. So now let's jump to the conclusions. So there are a few works that are studying architecture extraction properly. And because of model deployment, the attack surface related to threats targeting machine learning model confidentiality are significantly extended by side channel analysis. And what we want to point out through those works is that there's no need of complex exploitation methods such as heavy supervised profiling step in order to recover details about an architecture in the case that the implementation library that is used is known by the attacker, which corresponds to a realistic context, because the CMC library we mentioned is widely spread and widely used. And the point that architecture can be extracted this way is an important step in order to perform other kind of attacks, such as parameters extraction we mentioned in the beginning of this presentation. Despite some more complex cases, it still is possible to approximate those hyperparameters value or even handle those specific cases with more advanced tools such as pattern detection or even heavy profiling step that we mentioned before. And what this works highlight is the critical need to protect architecture from extraction, as it is a very sensitive point regarding machine learning model confidentiality, especially regarding 32-bit microcontrollers implementation, because it's representing hard challenges to develop efficient and practical countermeasure regarding parameters implementation and architecture extraction for those systems, as they represent important limitation regarding memory footprint and performance to be maintained. So here are the references I've used through this presentation, and thank you very much for your attention, and I will be pleased to answer your questions if you have any.
Questions? One?
About the countermeasures. Most of what you showed was, linked to execution time.
Yes.
So making this balance in the execution time, do you think it's possible?
You mean in the way that it should not be constant time regarding the execution? I think it could mitigate a bit those analysis. However, in this case, we simply use a single input in order to recover all the details regarding architecture. Based on the other papers, what I think would be efficient regarding electromagnetic emanation mitigation would be to merge, I would say, the execution of different layers one after the other, rather than keep the sequentiality of each of them and try to randomize it, I would say, in a way regarding the execution time. I hope it answers your questions.
Any other question? Yes.
You told that you deactivated the cache.
Yes.
What would you think would be the effect other than maybe introducing some delays and so needed to realign the trace? You think there would be another effect?
Yes, I think it would harden some cases, especially the cases that are already quite difficult regarding the extraction of number of neurons in dense layer. I think this would render those cases even more complicated. However, I'm not sure if regarding the convolutional layer, if it will introduce many differences, as the pattern we are looking at are very large, and I'm not sure, to be honest, I'm not sure what kind of differences it will introduce, and if what proportion of hyperparameters we are currently extracting would still be possible to be extracted or not. I'm not sure about that, but I think many of them would still be possible to be extracted simply with the naked eyes, I think.
Other questions? I have one quick one. I think about slide 11, but you do not need to go back.
All right.
You said something like it's since the code is open source, the attacker can make some prediction.
Yes.
So this sounds like open sourcing this thing is not good for protection. Is it true? Is it not true? What's your take?
I won't say that open source code is a bad thing regarding protection. However, I think we should be aware about the risk it represents, and we have to take that into account in order to develop proper countermeasure, especially for cases such as PAM architecture extraction, in which it seems to be pretty sensitive information. But I won't say it's a bad thing.
Thanks.